So, good morning all. So, sir, we are all live. So, I would like to invite Arpan Chattopadhyay to invite the speakers and start the session.
So, good morning, everybody. So, welcome to the first session of the last day of COMSNETs 2021. So, we have two tutorials today. The first one will be delivered by Dr. Sumit Darak from IIIT Delhi and Dr. Manjesh Hanawal from IIT Bombay. So, I will briefly introduce the two speakers and then I will pass it on to the speakers. So, Dr. Sumit Darak received his undergrad degree from EC in Pune University 2007 and PhD degree from the School of Computer Engineering, NTU Singapore in 2013. He is currently an associate professor at IIIT Delhi, Indraprastha Institute of Technology. Before joining IIIT Delhi, he worked as a postdoctoral researcher at the Commons Lab Excellence Center, Supelec, France, from March 2013 to November 2014. His research team is the recipient of DST Inspire Faculty Award 2005 15 to 20, Best Demo Award at CrownCom 2016, second Best Paper Award at IEEE DASC 2017, Young Scientist Paper Award at URSI 2014 and 2017, second Best Poster Award at COMSNETs 2019, and Best Paper Award at NCSIPA 2009. His team has received National Instruments Academic Research Grant 2017 and 18 and Core Research Grant from DST SERB India. Dr. Sumit is also a consultant on indigenous 5G base stations for VVDN technologies since March 2019. His current research interests include the design of efficient algorithms and mapping to reconfigurable and intelligent architectures for wireless and AI applications. So a hearty welcome to Sumit. So next I will introduce Manjesh. So Manjesh is a good old friend of mine. So we had a lot of overlap when we studied in IISc. And after that also, since we are working closely almost in the same area, so I know kind of well what he is doing of late. So Manjesh received his MSc from EC Department IISc in 2009 and the PhD from University of Avignon, France, with affiliation of INRIA Sofia Antipolis. He received his PhD in 2013. He has industry experience of a 2.5 years working experience as scientist B with the Center for Artificial Intelligence and Robotics, DRDO, between 2004 to 2007. He was a postdoctoral fellow at Boston University between 2014 to 15. Since 2016, he is a faculty in the Department of Industrial Engineering and Operations Research, or IEOR, at IIT Bombay. His research interests include performance evaluation, machine learning, and network economics. He is a recipient of Professor F.M. Moudawala Medal for Best MSc Thesis from the Division of Electrical Sciences, IISc, the Inspire Faculty Award from DST, and the Early Career Research Award from ACRB, India. He is recipient of Best Paper Award, honorable mention in COMSNETs 2018. So a hearty welcome to both of you, and I pass it on to you. Please start your slides.
Thanks a lot, Arpan. Thanks for the nice introduction. I am just sharing my screen now. I hope all of you can see my slides. Arpan, can you confirm you see my slides?
Yes.
Okay, we are good to start?
Yeah, please start.
Okay. Okay, so once again, I would like to thank this tutorial coaches, Professor Arpan and Nadeem for giving us this opportunity to present this tutorial here. Thank you, Arpan and Nadeem. So the talk of our title, as you all know, is like we are going to discuss about distributed learning in wireless networks. Okay, I also want to keep a watch on my clock so that we will be on time. Yeah, this talk we are going to deliver in two parts. The first part we are going to talk about multi-player multi-arm bandit framework for study of distributed learning in wireless network. This I'm going to cover in the first let's say 1 hour 40 minutes to let's say 1 hour 50 minutes. Subsequently, Sumit will take over and he is going to do the second part of this tutorial where he is going to talk about hardware architecture for this bandit algorithms. So first we are going to talk about various algorithms, their theoretical aspects, modeling assumption. Then Sumit will take you for the practical, like how to make them work in hardware. What are the complications there? Okay. So the rough outline of the talk is as follows. This talk will be divided in actually 4 parts. First, I will talk about distributed learning setup with the motivation and objective. Then we are going to talk about, so this I should be taking about let's say 15-20 minutes. And then we will move to single player bandits where I will introduce the classic bandit algorithms, few classic bandit algorithms and discuss the performance comparisons of theirs. Then we will move to the core part, the multiplayer bandits. And in that, we are going to talk specifically 2 cases called as homogeneous setting and heterogeneous setting. And in these 2 settings, lot of recent works has come up of late, especially in the last 2-3 years. We are going to discuss some of the recent advances and how to take the single player bandit to the multiplayer bandit case. Okay, so let's get started with what is this distributed setup we are talking about. Okay, so we all know that in a cellular network, the mostly the spectrum is licensed. Users connect to a base stations, and base station facilitates all the communication. So if you go see in the standard 5G standard, like there will be PUSCH and PDSCH, that is physical uplink shared channel and physical downlink shared channel, that will be used for data communication. Whereas this PDCCH, that is a personal, sorry, I should have said that personal control channel, personal downlink control channel, yeah, should be used by will be used by the base station to coordinate between the users by assigning which frequency channel they should be using, which time slot they should be using, how the users should time share and all. So if there is, let's say, k channels, they which can, some of them could be used for uplink and some could be downlink or maybe time shared, and let's say there is one control channel that will be available for the license user. But as we know, like in an most of the times, like some possibly this spectrum could be unused and maybe we want to unlicensed spectrum also latch onto this, but they also want to use it when these primary users are not active, right? But these unlicensed users, they have to deal with without any control channel, because base station is not going to facilitate them with any control channel, and they have to use channel whenever they're possible, they are free. For example, like you can think of like an ad hoc networks or like even IoT networks, right, where there is no central controller which is going to facilitate like through like this control channels. So in that case, uh, if the user's goal is to, let's say, they want to optimize their sum throughput, they have to somehow make a decision in a centralized way, and that is what our focus will be. And that is what we are going to, like, when without such a central infrastructure, when users are going to make a decision about their transmission, such decisions we are going to call it as like distributed decisions. And what is our goal? As I said, our goal is to maximize the sums rate of the secondary users. So henceforth, what I will do is, like, I don't talk about primary users, secondary users. Like as you see in the figure, like in the previous figure, like I had both primary users and secondary users here. Now I only move to, I just abstract the primary users out of the network. My focus will be only on the secondary users, and secondary users have only access to the data channel which they can use whenever it is available. So there is a no control channel here. Okay, so and secondary users, henceforth I simply call them as users in the network. Fine, we now understand, okay, without a help of a central controller we have to make a decision. But does this pose any challenges? Yes, there are a lot of challenges. And here, because there is no controller, like maybe channel information and all not easy to obtain, what users have to do is they have to somehow figure out which channel to use, and also they may not even know how many other users are there. Okay, and the worst thing is there is nothing to facilitate them to coordinate, like they can't even talk to each other or share information. And moreover, we are on a wireless network setting, and if two users happen to select the same channel, collision happened, and bad for all the colliding guys. They are going to not receive anything. For example, here I have depicted one case where, let's say there are six channels. If all the users, like six channels and three users, if all the users select different channels, all good. Like maybe their rates will go through. But if any two happens to select the same channel, boom, there is a collision and none of them are going to get. So this scenario need to be avoided, and these are some of the challenges that our distributed learning brings onto the table. Okay, so as you see, if the users has to kind of figure out what are the rates, then it is kind of unavoidable, right? The collusion has to happen in decentralized, because there is nobody to tell these users, okay, don't select the same channel. They have to select the things on their own, and they may eventually happen to selecting the same channel, collisions will happen. And we are in a wireless setting where most of the nodes or users are going to be will be powered using batteries, and any of these collisions are going to be bad, right? Because they are going to unnecessarily waste my battery power, and maybe my life of the nodes will come down. And this is where we are, like in the learning setup. Yes, if even though there is multiple players, but if there is some central controller to facilitate, things are a lot easier. But now once we are in a distributed setting, okay, what's happened, once we are in a distributed setting, things are going to be complicated. As I said, all this collision learning, all this has to be taken care, and that will be the focus of our talk. We are interested in learning algorithm, but we are focusing on the decentralized case, and we would like to generate or develop and study in this tutorial learning algorithm for such distributed setting.
Manjesh, your slides are not visible. I don't know. It is from my side.
Oh, is it? Were they visible, not visible right from the beginning, or only now?
No, just now it is.
I also can't see.
Oh, I see. Maybe looks like some issue. Like once my screen got locked, and once I again came back, you people are not able
I
to.
think you may have to reshare again.
Yeah. But okay, this I didn't realize. Otherwise, I would have put my screen lock time very high. Okay, just a minute. But Sumit, you may want to do this like for later purposes. Now it's hard for me to.
Yes.
You see it back?
Yes.
Okay. So yeah, this is what I was saying, that we are interested in this case where the users has to make decision in the decentralized fashion, and the case of centralized things are pretty easy, but whereas the decentralized brings its own set of challenges, and we are interested in developing distributed algorithm and analyze them to maximize some rate in this tutorial. Okay, some notations we are going to use throughout this um, tutorial is, like we are going to denote the number of channels as always like k, okay, and number of users as n, and we are going to assume that the rate that the user is going to achieve uh, on a particular channel, these are going to be denoted as mu ij. What is mu ij here? What is mu ij saying? Mu ij is saying the rate user I gets on channel j. And in such networks, right, we will be faced with a situation where the same numbers users need not be in the network all the time. Like new users may join the network, or some users may exit the network. So this will bring to like static and dynamic scenario for us, and that is another challenge in a distributed setting. And this we are going to call it as static and dynamic networks. Okay, static case where the number of users remains same throughout, and in the dynamic case they could be changing, like users could be coming in and leaving the network. So even though I am motivating this distributed learning as the case of particularly these ad hoc networks, IoTs, and cognitive radios, I mean, in general, you can think of other application as well. This need not be just restricted to this. For example, in a beam forming, like if multiple players has to form a beam, they should ensure that they all select the beam in different directions so that they don't interfere with each other. And interference could be like a thought of some kind of causing collisions or degrading our performance. Okay. Okay, one setting we just said is, the distributed setting we could be facing with static or dynamic network. Other possibilities, like we may be also facing this homogeneous versus heterogeneous network setting. What is this homogeneous versus heterogeneous setting? In the homogeneous setting, like all the users experience same channel behaviors. Okay, for example, let's say if I have two users and three base stations, and I kind of have a user one, user two get the same rates on different channels. For example, if user one and user two are going to communicate on particular channel, they both get a rate of mu1 on this channel. And if they are using let's say another channel, they will be getting, both will be getting the same mu2 rate if they are trying to transmit to this base station on channel 2, like that. Okay, so because of this, the rate in this can be characterized through a simple vector. Mu1 is the rate user is going to get on channel 1, mu2 is the rate user is going to channel 1, like that. So here I have to, from the learning perspective, I have to deal with one vector. Okay, this is the rate vector. And where the such scenario arise, homogeneous scenario can arise when, let's say, users are in a similar close proximity, and they kind of experience similar interference on the channels. So we can say that, okay, they are all going to see the same behavior on a channel. On the other hand, users not necessarily experience the same route on a given channel. For example, here user 1 and user 2 could be getting two different rates when they are going to transmit on particular channel. Okay, so because of this, you see that, like, if I have three channels and two users, the number of parameter in this going to be like 3 into 2, right? So in the homogeneous setting, the number of parameter is k, whereas the number of parameters I have to deal with in the heterogeneous setting is k into n, where n is the number of players. And where does this heterogeneous setting arise? I mean, you can imagine that when the users are far away, or they are in a different, slightly different congestion area or something, then the level of interference they are going to experience is different. So their gain could be potentially different. Now, as you see, from the learning perspective, the heterogeneous setting is going to be more complicated, right? Because here I have to deal with more parameters compared to the homogeneous setting. Okay, now what would be a goal in these setups? Now in all, this goal can be, like, we can think of two possible goals here. To define that, let's define an allocation. We are going to say pi is an allocation which is going to tell which user is assigned to which channel. And when we say allocation, we are going to take it as like orthogonal allocation, like each user is going to be assigned one unique channel. Now in this case, we can think of maximizing the sum rate in the network. So that is going to be like an optimal allocation. And in this, what we would be like to do is, like, this is the total sum rate in the network, and we would be interested in a policy or an allocation that maximizes this. So as you can see that this optimal allocation is nothing but a matching of a bipartite graph, right? So on one side you have uh, this channels, and the other side you have nodes, and you have to basically match which node to be assigned to which channel, and you want to do it in a such a ways that the sum rate going to get maximized. And so this, what ultimately we are interested is, we want to do this bipartite matching. So ultimately this distributed learning is now boiling down to what happened. I think I might have, did I lose again my share?
Yeah, you just need to do the full screen.
Oh, okay. Yeah, so what is happening is, if in this optimal allocation is nothing but, like, I want to do this distributed bipartite matching, and this problem is going to be like learning variant of basically bipartite matching graph. Now, why one should be only focusing on optimal allocation? One could be also think of stable allocation, right? What is a stable allocation? The stable allocation says that an allocation where no two users can simultaneously agree to swap channels without one of them getting less preferred channels. Okay, so this is like, you might have heard about all this marriage problem, right? Like, where the allocations happens like everybody, it is preferred that everybody gets the person who he likes, and if everybody is happy with the allocations, the matching they got, it is a stable. Like, if someone is not happy with the matching they got, it is going to be basically unstable. We can think of a similar criteria here. Like, since every user is trying to do make a decision on his own, like, he want to get a channel like where he thinks he is going to get a better rate, right? And those stable allocation can be defined in terms of potentials. So I'm going to define, I mean, this is just like a formal way of putting this stable allocation. You just it's just to enough to take this definition as like, no two players want to change their allocation. If that is the case, no two users want to swap their channels. If you are in such an allocation, that allocation is called stable allocation. Okay, so so the formal way of defining a stable allocation is, define for a policy pi, and for let's say some particular user n, define all the channels which are going to have a higher rate than the he is currently assigned. Recall that pi n is the channel he has been assigned, and this is the rate he is going to get, but there could be other channels where he is going to get a better rate. So this is going to be the sum for particular user, and if you are going to sum it over all players, this is going to be potential. And the formal way of defining allocation to be stable is that we are going to stay pi stable if swaps do not strictly reduce its potential. Okay, so we will be focusing on these two allocations. We will going to like mostly focusing on this optimal allocation, but briefly touch on stable allocation as well, because it do make sense whenever we are in a heterogeneous setting, right? Because if people are seeing different rates, and yeah, they want something better, whatever available. Now the question to all of you: which allocation is going? Are you going to think that is going to be hard to achieve? Like, we know we are in a distributed setting, things are going to be hard, but uh, given these two allocations, like if I want to achieve optimal allocation and I want to achieve stable allocation, which one is good? I want to see if there is something in the chat. Yeah, just want to give a minute. Yeah, people are saying, I see two responses here. People are saying stable allocation is hard, Think about it a bit more, like why you think stable allocation is going to be hard. Optimal is harder. Someone is saying optimal is harder. Yeah, I see two responses which say optimal is harder. Can anybody just give a line like saying that why you think so? Like why you think optimal is harder and stable is easy, or why if you think the other way, why it is so? Anyone want to put their thoughts here? Yeah, Tony says optimal needs global knowledge, and the stable really don't need that knowledge, right? Table just need to know yes no kind of answers, like uh, all they have to tell, like whether okay, given another channel, do I prefer that or not. Only that kind of information is required in stable allocation to reach a stable allocation. But if you want to reach an optimal allocation, every players need to know what is the rates the other players are getting on that channel or on all the channels. So, as Tony correctly pointed out, optimal allocation needs kind of global knowledge, and in a distributed setting, that's very hard to get right. Like, what all I can do is like I can know what's happening with me, like what kind of rates I'm going to get. Since there is no way I can talk to others, I can't get like what others are experiencing. But maybe like if I have to just ask yes no questions to them, like okay, do you prefer, do you like if I want to ask other guy, do you want to take my channel, like this is like a small bit of communication, right? Maybe just yes no kind of questions. Maybe this is maybe possible, like even though there is no dedicated channel, maybe like maybe possible to exchange one bit of information. Whereas getting an optimal allocation needs like the full like actual value the others are experiencing. Okay, Abdul Rahman Sattar asks, should not the allocation function also have a time parameter? Yes, we will come to that, but I'm just talking about like one time, like uh, if let's say you have in one round you want to do this, so how we are going to do that? Okay, all this time dependency will come. Yeah, Bignaraj Panigrahi says stable is harder, but I mean, not really uh, Bignaraj. Like we just argued that stable may be a little easier. Like we will, as we go along, you will see that. Okay. So here is another like example to motivate this concept. I have given a simple case of two users and three channels here, and we want to see like distinguish optimal allocation from a stable allocation. Okay, first consider the case like user 1 is allocated channel 2 and user 2 is allocated channel 1. So in sum, they are going to get a value of zero point 0.7 plus zero point 0.5, that is going to be 1.2, right? Yeah. Uh, is that an optimal allocation? Or is there anything that better you can get here? You can verify that that's the best we can get. So if you look into this matrix, you may feel that okay, zero point 0.7, zero point 0.7 gives me 1.4, which is higher than 1.2, but that is not going to be a valid allocation because I can't give both user 1 and user 2 the same channel. They have to be on two different channels. Like if both U1 and U2 take the same channel, actually they are getting zero because they are colliding and none of them get anything. Okay, now let's take another allocation. Let's say user 1 gets channel 2 and user 2 gets channel 3. So in sum, they are going to get a zero point 0.7 and plus zero point 0.4, that is a 1.1. Now the question is, definitely this is not optimal allocation because in the optimal allocation, I'm getting a value of 1.2. It can't be optimal allocation. The question is it a stable allocation? And you can verify that it is indeed a stable allocation because if you are going to swap, now user 1 got this channel and user 2 got this channel. Now if you are going to swap them, user now 1 is going to get channel 3 and user 2 is going to get channel 2, where they will be ending up with 1.3. No, I'm making something mistake. So actually I have made a wrong computation. You see that? What is the optimal allocation you get in this channel? Do anybody see that? Okay. So the first optimal allocation is wrong. Can anybody confirm why is the first allocation is wrong? Is this an what is will be the optimal allocation here? Suppose, let's say, let me do this. If user 1 gets C2 and user 2 get C3, or let's say user 1 gets C3 and user get C2, he is going to get a value of 1.3, right? So the optimal allocation is user 1 gets C3 and user 2 gets C2. And in this case, sum rate is going to be 1.3. That is going to be the optimal allocation. Now, because of that, this is not going to be a stable allocation, right? Because if you are going to get U1 is going to get C2 and U2 is going to get C3. Now, if you swap, you are going to end up in this, right? And that is like an optimal allocation. So this is not actually, this is also not a stable allocation. So this computation is wrong here. I will just add that remark. Okay, now let me ask this question. I hope this optimal allocation notion is clear from here. Now suppose I give you this one. Now suppose I ask you this allocation now. User 1 is given channel 1 and user 2 is given channel 3. So the sum rate is 0.9. And if you are going to swap these channels, then user 1 is going to get C3 and user 2 is going to get 0.5. They are going to get a higher rate, right? 1.1. So that is not going to be a stable allocation. Now, based on this argument, let me ask you this question. Let's say user 1 is given channel C3 and user 2 is given channel 1. Now, can you tell me, is this a stable allocation? For this last one, I want to see if somebody is able to do this. User 1 gets C3 and user 2 gets C1. And now if you are going to swap, is this swap will be mutually acceptable to them? Yeah, Brijesh and Pawan says not stable, but Shipra feels that it's a stable. Shipra, can you justify why you think it's a stable one? Yeah, Shipra, just to verify that it is obvious that if you are going to, like if I'm going, user 1 is getting C3, right? He got a 0.6 and user 2 got C1. So they have got a value of 0.6 and 0.5. If you have to swap, then user 1 has to go to channel 1 and user 2 has to go to channel 3. So user 2 is getting something bad and their sum is now gone from 1.1 to 0.9. So obviously this is not going to be stable, right? Okay, so as you see that stable allocation can be going to give a lower value than the optimal allocation, but we just noticed that stable allocation can be possibly easier to achieve in a distributed setting. And even though the stable allocation is something not giving good, right? Maybe you want to leave it that because it's easier to achieve. Okay. Now, coming to optimal allocation. How are going to evaluate the performance of a policy if your goal is to achieve the optimal allocation? So this is where time dependency comes, because now I'm in a learning setting. I want to learn the optimal allocation. Okay. So now let's say that my policy is something which is going to decide which channel to select in round T based on my past observations. I'm going to denote that as pi ti. And over a time period of T rounds, let's say this is the policy used, pi 1, pi 2, all the way up to pi T. Now I'm going to define my regret as following. The first part here is the total rate I'm going to get when I'm going to use the best policy, right? Because this pi t star, like I've already denoted, pi star is the optimal strategy. Like it kinds of knows what are the rates and always assigns to each user a channel that is going to give him the best possible rate in this optimal allocation. And this is the total rate I'm going to get over period t, and this is the best possible I get, and what I am going to compare it with is what I obtain. So my policy pi is going to select this channel for user I in round T, and this is going to be my total rate I'm going to get. But also notice that there is a factor of 1 minus eta here. What is eta? Eta is like a collision indicator. If it is going to be 1 if player incurs a collision, otherwise it is going to be 0. Right? So notice that in this policy pi star, there is not going to be any collision, because the optimal ones always allocate the channels which are distinct. That is, the allocation is going to be orthogonal. Whereas when you are going to learn, and you are making a decision in a distributed fashion, you may be incurring collisions. And in some rounds, you may be actually not getting anything, like when you incur a collision. So this is the policy reward I'm going to get, total reward from my policy, and this is what I would have gotten. Okay. And in addition to this regret, we will be also interested in the total collisions I'm going to incur in the network. And that collisions is simply the count of the total collisions I'm going to incur across all the players, across all the rounds. Okay. And what will be our goal in this case? Our goal is going to be find a policy that is going to minimize this expected regret. And also I want to keep a check on how many collisions that algorithm or that policy is going to incur as we keep running this algorithm. Okay, now let's think about the stable allocation. Fine, whenever it is optimal allocation, we just set up our criteria like this, like, okay, I want to minimize regret and all. But when it is stable allocation, what should be our criteria? First thing, as we discussed in the example, like there could be multiple stable allocations. Okay, because you may end up in many allocations that are actually stable. Okay, and there is no way we can come out of, right? Like once you are in a stable allocation, you will stick to that. And this different stable allocation can give different sum rates. It's not necessary that, like, even though there could be multiple optimal allocation, but all the optimal allocation will give the same reward, some reward. But the stable allocations all the stable allocation need not give the same sum reward. Then the question arises, like, if I'm target is a good stable allocation, which one do I compare with? Because there are so many possible stable allocation and with the different sum weight. But instead of worrying about all this, like which one do I compare with, which I should take it as a benchmark, what we will be interested is, we will be interested in a learning policy when stable allocation our criteria is just like, I want to quickly reach a stable allocation. whichever it is. Like we know some of the stable allocations can be suboptimal, and some of them can be in fact very bad, but fine. All I care here is when stable allocation is my criteria, I want to quickly go and achieve it. Okay, so let me see if I have any questions or comments at this point. Okay. Okay, let me see. Okay, Shipra said, okay, I'm going to start from Srinath's comment. Stable. Okay, Srinath, I'm skipping this because we already moved ahead of that. Okay, now Tony's question is why the collision is indexed by J, not I. Okay, so what is the index J we are using? The index J is, okay, let me go back. So basically we are indexing our player, like say like this J here, like sometimes maybe I made a mistake here. This should have been I here. I here, okay. Yes, thanks for catching that typo. Like basically we are saying a player gets a collision or not. And if uh, and we are going to see like how many players got the collision. Okay, not like, yes, we can say like a collision happened on a channel, or we can ask the question whether the collision is experienced by an user. We are going to keep track of how many collisions user incurred, because what we said earlier, the collisions is going to cost energy, right? We want to see like how much of energy cost wasted in the network, and that is why we will keep track of how many collisions like in total incurred by the users. I hope that clarifies, Tony. Okay. The best rate policy is static policy, is not. See, like what we want to do, like as you see, like as a bit like Pawan, as you see, as we go a bit more into this actual algorithm, you see that when we are going to do learn, we can't like there can't be static policy. Like maybe there is some, you will see some notion of exploration will be there, but what we are interested in, the aggregated rate, how close it is coming to the oracle rate. And that we will be also interested how much this deviation, as we are going to consider large number of rounds. Okay, so time index is still there because we are going to, my policy is evolving as we go, right? Like as I get more and more information, I'm going to update my policy, and so my channel selection strategy can vary. So there will be time index there. In my learning, I'm never going to stick to one allocation, and in fact, as I get more and information, I'm going to update, and that is one of the fundamental aspects of this online learning. And also, like Tony's want to comment that okay, the available channels are changing due to primary users. Okay, the channels are okay. What do you mean? What you mean by available channels are changing? See, the number of channels is going to be fixed. We are saying there is k number of channels, and if the number of users are going to be more, obviously more channel will be occupied and less number will be available. I don't know if that is what you mean. As we are going to take that the number of channel is going to be fixed in this. Okay. Now let me move back to the slides here. Okay. Okay, now let's get on to this learning aspect. So far, we have been just defining, okay, what would be our criteria, how I am going to uh, define or evaluate my policy. We have defined in terms of regret, and we defined in terms of sample complexity and all, right? Just a minute, I need to switch off this. So now let's bit strip down, and instead of going into the multiplayer, considering already too many players, let's focus on the single player case, which is kind of well studied. Now I'm just going to give a quick overview of what's happening in this single player case. So we are saying that, okay, just assume that in this network there is only one user, and he has all this channel available to him to transfer. Okay, so now I don't need to really, on the single player case, I really don't need to worry about heterogeneous, homogeneous case, right, or static case. It is static, and it's by definition it's a homogeneous, because there is only one player and he's going to see some rates on the channels. Now, what is the standard single player setting? We can think of single player setting as like a standard multi-bandit problem. So where we can say that, like, okay, each channel is going to be certain rate according to some distribution mu, nu, and which has a certain mean mu k. And if k is played in round t, the player is going to observe a reward xkt, which is drawn from nu k. It should have been nu k here. Okay, so whatever that underlying distribution associated with that arm is going to draw a sample according to that. And this is one of the fundamental, like basic assumptions in this bandit setting, that whenever I'm going to pull an arm, I'm going to get a sample which is independent across all the arms and across the past observations I got. Even though when you're going to pull an arm, the underlying distributions from which the samples come is the same, but these samples are generated independently each time. And now our policy is going to be, in round T, a player is going to select a channel pi t based on his past observation. And here the expected regret of a policy we are going to define as simply this. So if I know all the parameters mu I, what I'll be doing is I'll be playing the one which has the highest value. So I'll be getting over a time period t, this is my total reward. Whereas if I have to play with my policy pi, this will be what will be selected in pi t, is what I'll be selecting in round t, and this is going to be my expected cumulated reward. And here expectation here is with respect to the randomness of these pulls, because my as sample comes, that is going to induce some randomness in the way I'm going to pull my arms. And as you see, like, I'm already interchangingly using these terms, channels and arms, right? Like henceforth, when we are going to now talk about, once we have mapped this to multi-arm bandit setting, I'm going to call channels as simply arms. Okay, now talking about this setup, single player setup. One of the fundamental things in this online learning setup or multi-arm bandit setup is exploration versus exploitation. Let's see this a bit more. Okay, now we have set up our criteria as to minimize this regret. How to do that? I don't know anything. Even I'm in a single player setting, I still don't know anything, right? I don't know which channel is better. One obvious thing we can do is, as a one simple policy is, don't consider any observation, just pull each one of them equal number of times. So you have t rounds and k arms, pull each one of them t by k rounds. So this is like explore each arm equally. Maybe is this going to be a good strategy? Not really, right? Because maybe one arm is good, like you are treating that good arm same as any bad arm. You are giving the same preference to everybody, so you may not get anything good from this. Other thing is, like, try to be greedy. Use information, the samples you are going to collect. Every time you can update the empirical means as soon as you get a sample. And let's call that an exploit the best arm strategy, that is policy 2. Will that policy be good? Again, this need not be a good policy, because like it may happen that a bad arm initially give a good value, and the good one actually give you a bad value, and because of that you may get stuck to playing all the time bad arm, and you are going to do very bad because of that. Otherwise, don't do like the extreme policy 1 and policy 2. Try to like balance between them. So in this case, what you can do is like you explore for certain fraction of t rounds, that is epsilon t, and after that you exploit. And these are like called such strategies are called usually like explore then exploit. Maybe like when you are going to explore, you kind of have given collected sufficient samples of every arm, and when you estimate their empirical values, maybe like you will be able to identify the good one. Okay, but yes, this policy 3 looks reasonable, but I mean, how to choose this epsilon? That's a bottleneck here, right? I said epsilon, but how much I should explore, and at what point I should stop exploring and exploiting. So as you kind of get intuitive feel that if I'm going to explore too much or stop exploration prematurely, both situations are not good. Like exploration high, uh, what will happen if you are going to explore too much? You will be left with too few rounds to do the exploitation. On the other hand, if you stop your exploration earlier and you go for premature exploitation, then maybe like you didn't have sufficient samples and your empirical estimates were not good up, and you may end up missing the optimal action. Now the question is how to choose epsilon. So here I have just like put some toy example here. Like I have taken 5 arms with this different values of mean, and set the t equals to 10,000. And you see that like if I know this optimal value 0.8, like is 0.8, I'm always going to play this arm, and over 10,000 rounds I would have got like about 80,000 sorry 8,000 as my total reward. On the other hand, like if I can like do this exploit only when I set epsilon equals to 0, like where I start do greedily and I do like explore equals to 1, that means I'm going to use policy 1 all the time exploring. Like seems they are like at too extreme. And if I'm going to change this epsilon, play with this epsilon, you see that by setting epsilon something between 0 and 1, I'm getting a slightly better reward, cumulative reward, right? And this is what somehow tells that I need to be selecting this epsilon in a better fashion. Now the question is exactly how to select this epsilon. I don't know anything about, I'm a single player, but I don't have any information about these games, how to do this. Now, this has been what kind of how to do this, like how to do this, like without knowing in the channel rates, how to get the optimal, how to accumulate more and more reward. This has been a very fascinating question many times, and this has been said that like see like there is no way in these problems you can stop exploitation, like however sorry exploration, like however uh, it is better like as you go like collect more and more sample, you should be like you can't be at any point you can't be 100% sure that yes I have gotten the optimal one, because you are in a stochastic setting, and you can be by central limit theorem like you can be confident only as at t tends to infinity, and that is not the case. Like when we are going to do finite samples, you are never going to be confident what is that, because you want to keep collecting more, so the exploration never ends. And this has been, in fact, formalized by Lai and Robin in one of the famous results. It says that any policy is going to be incurring a regret that is like growing like this, log t, divided by this divergence. The d mu I mu star is going to define the divergence between this mu and mu star. And this result basically says that like, okay, your regret is going to be like lower bounded by something, and any policy you can't expect to do better than this. This bound is going to be called as problem dependent because this works on a particular value of mu. So what is the notation I have used? I have used mu star to denote the optimal value of mu I, and I star to denote the index of the optimal arm. And the delta I is the gap between how far the mean of the ith term from the optimal one, and delta I'm going to denote is like the smallest gap, and often this delta here is called as a suboptimality gap. So as you see that like this bound depends on a given problem instance. Like if you tell me mu, then this bound is characterized in terms of that. And there has been also a bound which is called problem independent or gap free bounds, which tells that no matter what is your problem instance, so sorry, no matter what is your algorithm, I can always find a distribution which is going to make your algorithm suffer a regret, which is going to grow like square root kt. And this has been known as like problem independent bound. So whenever we want to develop algorithm, we want to keep these fundamental limits in mind, and we want to see that like definitely we don't aspire to like beat this because these are fundamental limits. We want to develop algorithms and see like how far we can uh, like minimize the regret so that it achieves this lower bounds. Okay, maybe I'll just cover this one and then talk. I mean, maybe then look for some if you have any questions, clarifications. Now let's revisit my explore and exploitation I was talking about, right? So fundamental results say that like, okay, you have to be kind of doing continuously exploration. There is no way you can stop anytime. So let's say that, but so I have to basically kind of balance this exploration and exploitation well. Is there something I can do along those lines? So this is one of the simple algorithm called explore then commit algorithm. What one can do in this is like, we are going to play the arms, each arms certain number of rounds, that is going denoted by m. So my policy pi t is such that till mk rounds I am going to play these arms in a round robin fashion. So after this mk rounds, I would have played each of the k arms m number of times. And after that happens, what I'm going to do subsequently, I'm going to commit to an algorithm which I found to be optimal at the end of mk rounds. So here the t is exactly mk here. Whatever I'm going to get after mk rounds, I'm going to find the maximum value of that and always fix with that. So this I should have, instead of t, I should have just made it mk here. So that is whatever I get the optimal one by the end of mk round, that is what I'm going to play. So that is why this is explore, and after that you are going to commit. Now, if you are going to look into the regret bound of this, I mean this, okay, so some things like which I'm going to use consistently in this, whenever I'm going to write mu hat, that is basically the sample mean of the observations I got for particular arm I. And ti, I'm going to denote to count how many times I have pulled arm I till round t. So now if you are going to little bit do analysis, assuming that these are all like some sub-Gaussian random variables, this random variables coming from, you will be able to characterize this regret bound like this. So here, the first part here basically corresponds to the regret you are going to do in the MK rounds, and this is the regret, your expected regret you are going to get subsequently, like after MK rounds. Now you see that if this m is large, this quantity is going to dominate and this quantity is going to come down. On the other hand, if this m is small, this is going to be smaller, yes, but this quantity could be greater, right? See, this is minus and minus m here also. So in that case, your exploitation value you are going to get is going to be bad. So then, is there a way like I can tweak this m that is exactly going to tell me how I should be balancing my exploration and exploitation? In fact, if you are just going to optimize this, treating this m as a continuous value here for k equals to 2 case, like 2 arm case, you will be end up finding that m is going to be this value. But notice that m depends on this gap here. So if I somehow tell you delta, you can find how you should be finding this m and plugging in, you are going to get this kind of bound, which is like square root t. And this we already know is kind of optimal. Okay, so let me take a short pause here and see if there are questions, and we need to accelerate now. Yeah, I see some. Okay. Um, okay, 2 minutes. Okay. What is that? Abdul is asking, why do you have an expectation in the optimal policy equation? Which one you are referring? Let me go back and see that. Uh, yeah. So here, see, this is the expected best rate I'm going to get. And here I put expectation here because my pi, the channel allocations, it is going to be induced by the sample path I have been seeing right in the past. So this allocation, if you are going to run this algorithm again, you are going to possibly see a different history, and the allocations in each round could be potentially need not be the same values. So that is what the randomness induces. That is why this expectation has come. I don't know, because this question is only left at that point. This is what you meant. Okay, so app, I meant eta should be indexed by a. Yes, Tony, that I mean you are referring to the user here. Yes, it should be indexed by user. Is the policy value a probability value indicating probability that the channel is assigned to the user? No, no, Uttara, this is not the case. Like it is, we are not talking about the probabilities here. The kind of policies uh, we would be interested in, like given you are going to observe the history so far, right, till any round, you are going to observe that round, and you are going to kind of assign some value to each of these policies, each of these arms, and then you are going to choose one from them. Okay, we will become a bit more clear when I talk about specifically policies. Yeah, as of now, yes, there are variants where you would be want to choose them probabilistically, and that happens usually in the adversarial case. But now mostly I'm focusing on the stochastic case, where I don't need to do this. I don't need to like really induce further randomness in whatever the policy asked me to play. Okay. Again, Tony is asking. Okay, he was asking you about the optimal, not the user's policy. Okay. Okay. Divankar is asking, why don't we learn epsilon itself? Yeah, let's say the epsilon is a quantity between 0 1, right? Like see that epsilon, now you are trying to learn epsilon which is over an interval, that is going to be much harder, right? Like choosing something, like there are infinitely, like uncountably many epsilons are possible, so that's why you don't may want to go with that. Okay, Rahul Meshram. Rahul. Oh, hi Rahul, you are the same Meshram who was at ITB, I guess. It's the same. Okay. Just clarification. Lower bounds. Oh, okay. Hi Rahul. Lower. Just classic clarification. Lower bounds do not make any on the distribution. Do not make any. What do you mean by do not make any? Uh, Yeah, like this lower bounds, like I didn't go into the details of Lai Robbins lower bound. That they, when they proved this lower bound, that they had defined it for some class of distributions, like basically parametric distributions. So like as long as you should be able to parameterize your distributions, I think that should be fine. And we would be mostly looking into parameterized distribution, so that we should be fine. Okay, so I hope that's what you meant. Okay. If there are no other further questions, let's move on. Okay, so we'll speed up so that we have more time for Sumit as well. Okay, now let's now focus on, like somebody asked me, like this policy is going to be playing these arms in a randomizing way or something. So let's make that bit more precise. Now we'll come to like how the arms will be selected in the single player strategy. So in the single player, broadly there are two ideas. One is called optimism in the face of uncertainty principle, and another is the Bayesian approach. So let's get started with this optimism principle. It says that as you play along, you construct confidence intervals for each arm, right? So here for I term, you are constructing a confidence interval. The lower one is denoted by lower confidence bound term, and the upper one is going to be UCB term. So this is like a just pictorial snapshot of that. Like when let's say this this central dots are the actual mean values and the bars are the estimates, and you are going to have some interval which is going to tell like what is your confidence interval around that. This upper portion is the upper confidence value and the lower portion is your lower confidence bound. Now what this optimism in the face of uncertainty tell you, like given this kind of intervals, confidence interval you have, just assume that this parameter, the true value, is actually this value itself. Like I'm going to like assume that, okay, I'm going to get the, I just want to be more optimistic. Okay, this is the bound I got on the estimate. So I'm going to take the best possible value that bound is telling. And now I'm going to select an arm which is going to give me the highest value of this. And usually such policies are going to be called as index. Like basically you are assigning an index to each arm and you are going to select an arm which has the highest index. And here the index is basically the upper confidence bound we have. Now one of the famous algorithm based on this optimism in the face of uncertainty is what is called upper confidence bound algorithm itself, which has been named UCB1. And it is going to take the upper confidence bound in this fashion, where mu I hat is basically the estimate you have till that round for arm I, and this is the confidence term. And this confidence term is basically comes from Hoeffding's inequality. And here the assumption is like your distributions have bounded support. So this is like, you see that, right? Like this UCB, this index is what doing, it is taking into account what is your current estimate and also this confidence term. And this confidence term is going to shrink if you have more number of plays. Okay, and this capital key can also be replaced by small t. Okay, so now it is kind of, this alpha is kind of trading off. This is kind of telling how whether you should be going for exploitation, and this term is basically telling, this is the confidence term, this whether it is showing you should be doing exploration, and it is telling you how to trade off. So what this UCB algorithm simply does is in each round it computes this UCB index and then play the arm. So I should have made this maximum value here like like it is going to take the maximum value of this UCB index and then play and observe the sample from this. Now for this algorithm, it has been well established that it is going to give me a regret which is like a log t by del I. Del I is the gap, right? And its problem indemnity bound is like this. So if you just look into this, like yeah, this is does not look as same as the lower bound, but this is in terms of t, it is similar to what happened in the lower bound. But whereas this problem independent bound, except for this log t factor, this is going to be optimal. Okay, now another famous algorithm based again on this UCB idea is called the KL-UCB. KL stands for the KL divergence, we said. And it is going to compute this UCB, the upper confidence bound, in a slightly different fashion. This is coming from another set of concentration bounds. It is going to say that at any point you have this estimate and you compute a Q which is going to satisfy this condition. And one can show that the confidence intervals you are going to compute based on this KL-UCB based one is going to be strictly contained in the confidence interval bounds you are going to contain, you are going to derive for the UCB. So this KL-UCB based confidence bounds can be better. Okay, and it has the regret bounds have been also established and well studied for this KL-UCB. And for this, the upper bound, if you are going to play now the arms based on this UCB index, it has been shown that your regret bound is going to be follow this value. which is exactly the lower bound we have. Hence, this bound is like optimal. So we have to like think all this optimality in asymptotic sense, but I'm talking loosely, like even in the finite round, these are all like optimal. And problem independent bounds can also be shown. So this is again optimal up to lofty term. So this UCB algorithm, UCB1 algorithm, KL-UCB, these are based on what I called as optimism in the face of uncertainty. And there is another class of algorithm called based on the Bayesian approach. So what we did in optimism in the face of uncertainty, we assume that the distribution parameters are unknown, but they're fixed. Once you start the problem, these values are fixed and you need to kind of figure out as you learn. And most of the times these are done like by computing this mean values, right? We're computing these mean values and having these confidence bounds. So this can be like, these are all like maximum likelihood estimator methods, and these are like basically counting, based on counting, and this often called as frequentist method. On the other hand, what Bayesian approach does is like it don't assume that the parameters are fixed a priori. It assumes that they are themselves are drawn from another distribution, and based on the observation you are got, you are going to update the posterior distributions. Okay, so you are going to assume that these values of the associated the parameters, they will be drawn from some distribution conditioned on like what are the sample you are going to observe, and you are going to keep updating your prior distribution to posterior as you are going to get the samples from the observations. Okay, so there is one famous, I'm sure most of you would have heard and possibly implemented also. Like I'm just going to talk about one Thompson sampling for especially Bernoulli distributions here. So in this, the posterior distribution is going to be computed. Like this prior and posteriors, they are going to be assumed to following. The prior is taken to be a beta, and we know that when we have a beta distribution, the posterior is also going to be beta distribution itself. And based on this, we are going to take this. Just a minute, I need to stop this. Okay, so we have this beta function. What it is going to do is we are going to take since it's a Bernoulli distribution, whatever the sample I have observed till time t, I'm going to count. This is going to give me basically the number of ones I observed, and this one I subtract the number of ones I observed from the total number of samples. This is going to give me the number of failures. And this is how the beta distributions are updated. And how the Thompson sampling works. Thompson sampling works by keeping track of the number of success failures of each arms when you are going to pull, and based on that it is going to compute the values mu i's. So here mu I hats are going to be drawn from beta distributions depending on your success and failure. And again, it is once it is still the next part it is going to do as it in the optimism principle. It is going to take the one with the highest index. Okay, and once it takes, it observes the sample and then going to update and repeat this process. So as you see that we have not like randomizing anything like either in this strategy, right? That we are not doing any randomizers. Whatever the values these algorithms give based on the UCB index and maximization of those values, we are just going to play them. Okay, I think that was one question someone was asking earlier. Okay, now again, this problem is also well studied now. Its regret bounds have been shown, like as you see that its regret bound is now given in terms of this. This is actually the optimal value, and the problem independent bound is again square root kt, and this is optimal up to this factor log t. Okay, here I am just giving you some comparison about how these algorithms behave. Like here, you see that like I have taken this particular problem instance. I have drawn these curves for UCB, Thompson sampling, and KL-UCB. You see that KL-UCB is actually doing better than UCB, and Thompson sample is doing even better than KL-UCB. This is in general the case most of the times. You will see in the problem you incur Thompson sampling does better than, and here this pool, this regret bound is indeed justified by the number of pools. So you see that as algorithm is running, I'm just keeping track of uh, how many times each arms is pulled. UCB pulls the optimal arm, let me see, around 1300 times, whereas this guy pulls around 1700 times, whereas the Thompson sampling pulls it 1800 times. So obviously more times the optimal arm is pulled, more better is the regret, and that is what you are capturing. And also this is like a one snap, some simulation which shows like how the uh, confidence interval varies. So more an arm is fold, more smaller is going to be its confidence interval, right? So you see that this arm by UCB is pulled more number of times, it has this confidence bound, but KLUCB pulls that more number of times than the UCB, so it has still a smaller confidence bound. Okay. uh, Okay, but it is now in question. Then the question that comes to mind is it like I should always go for Thompson sampling? That's not always the case, and it has been discussed in papers, right? In some cases where the the difference in the means of the arms is very small, Thompson sampling may not give advantage, and in that case, you may want to like think about, okay, which algorithm to use. That brings us to this comparison, like, okay, we have these three algorithms, which one to go for? Here I have put some advantage and disadvantage this algorithm. UCB1, as you see, it is a simple calculation. There is nothing like, you just need to compute index of each algorithm and find its which is the maximum. So this is pretty easy to implement. What is small disadvantage with this is that, yeah, it has a tuning parameter alpha, right, which we need to set how to trade off between exploration and exploitation. Yeah, another parameter, another disadvantage we see, like sometimes, I mean, it does poorly compared to KLUCB and Thompson sampling, when even though it is like kind of has a optimal bounds and all, but not empirically, it's not always good. Now, what are the advantage, disadvantage KLUCB? The KLUCB, as we see, like it is optimal, and it has indeed a good empirical performance compared to UCB1. But what's the issue with this KLUCB is, like, as you see, like we have to solve this optimization problem. Even though it is a nice convex problem, but you need to solve this in every round. And if you have to run this in either software or like in hardware, this is going to be too time consuming. Like when I give this KLUCB algorithm to implement in my course, like people say when they implement even in Python, they say it takes a lot of time. If that's the case, you can imagine like this is going to be even harder to implement in hardware, right? Because optimization, like Sumit will convince you later that hardware don't like optimization. Uh, and another one is like Thompson sampling. Yeah, we saw that Thompson lacks many good things, like it has no tuning property, it is asymptotically optimal, it has good empirical performance, but it's again has a disadvantage. Like as you see, it is a Bayesian approach, and it every round it has to kind of maintain a posterior distributions, right? Like every time you observe a new sample, you have to update your posterior distribution, and then just select an index from this posterior distribution. So if you have to do it in hardware, maybe this is simpler in the software, like your code will do it very fast. But if you have to do it in hardware, doing this, generating this randomness is hard. Again, Sumit will argue this, like because of this, even though KLUCB and Thompson samplings are good in terms of empirical performance, because of their involvement, maybe it's hard to realize them in a hardware, and maybe one has to do some choice between which one to go if you want to trade off the complexity. So there are other algorithms called UCB tuned, UCBV, and MOS. Like I will not go into that. Okay, fine. So this is like basically the primer I wanted to give you on this single player case. Like we just talked about these three algorithms which are popular. uh, Now we want to move on to the multiplayer setting, and now we want to see that how to leverage the knowledge we have gained from the single player to the multiplayer case. Okay, at this point, let me see. Let's see if there are any questions. Uh, okay, I should be looking into the question or chat window. Yeah, Bignar. Okay, Panigrahi is asking how to distinguish between stable versus unstable in real time scenario. uh, how to distinguish, like you see that, right? The allocation don't remain same. Like if it is an unstable, maybe in the next round itself the allocation will change. That is an obvious indication that this is not a stable. Like if at least for a few rounds your allocation is going to be the same, that's a kind of giving you an indication, right? It is going to be stable. What is this again? Should not allocation. Okay. uh, Okay, I see some question. I don't know what is this. What is this? Point 0.6 plus points. Okay, okay. Somebody is putting it differently. Okay, fine. I think these are all previous questions. So I will continue. So I see no questions. I will just continue with this. Okay, now let's come to homogeneous setting. Like how about 40 minutes? Let me see how I can run through this. As I said, when we have multiple players and we are in a distributed setting, we don't have any central coordinator, so players can't communicate. And we argued that collisions are unavoidable in this case. And when a collision happens, this loss of battery power happens. And in the multiplayer case, we are also faced with the static versus dynamic case, and also homogeneous versus heterogeneous case. So now explicitly let's focus on the homogeneous reward case. So here recall that when I say homogeneous, like each player sees same mean vector on its channels. So if both players transmit on channel, else they are going to say the same uh, mean value. They experience the same. Now let me take this n star as the top n channels. So what I mean by top n arms, like you have, let's say, k arms, order them according to their probability vectors, and the top when you order them, the top n listed ones, call it as top n arms. Now if I just tell you, okay, take me this mean values, I just give you this mean vector and tell you that there are n users, what is your optimal policy is going to be? Can somebody think about what will be the optimal policy here? So in a homogeneous setting, what would be the optimal policy? Sumit, am I audible? Arpan?
Yes, yes, you are audible.
Okay. Yes. So when we have this homogeneous setting, the obvious policy here is, if you also identify the top n arms, give one arms to each player. And then the follow-up question is, does it matter if as long as I give this n channels, top n channels to n user, does it matter which channel who got? So obviously, right? Like, yeah, it does not matter like you gave to which one, because all I care is a sum rate. And that is one of the simplifying things in the homogeneous setting. Okay. So then in this case is simply each player is assigned one arm from the top n arms. Now, because of this, like now we can simplify the regret. Now, the best rate one can get is just like assign each user one of the top n arms, and this is going to be the total uh, reward you are going to get by applying your policy. And because there could be a collision, that collision indicator is here. Yeah, I think here I have denoted this index correctly. So here J is denoting the user index, and this collision is going to be uh, I'm going to keep, every user is going to keep track of his own collisions. And this is the total collision induced. And in this again, like our goal is to like how to minimize this regret, keeping my total collisions low. Now, okay, what one can expect in this multiplayer case? Like in the single player case, Lion Robbins result told us what should we expect. Now, when we are in the multiplayer case, what should we be expecting? Now, this multiplayer bandits is equivalent to a single player bandits if there is a central controller. Like if there is a central controller, he can tell all the players which arms to take, and he will only tell the players to take the orthogonal set. So in that case, all the central controller is need to do is identify the top n arms. So then it is like just boils down to a single player case. So in this case, it has been shown again that, so this problem now is equivalent to like a one player identifying the top n arms. So this is what famously called, popularly called as multiplay bandits. And for this multiplay bandits, a following regret bound has been established. So what is this? Like this is almost same as that of the live Robin result, but except for the fact that now I is starting from n star. Okay, so I am going to, so it is just n, not n star here. I'm going to make for the here an assumption that the just for convenience that my mean values are organized in this, like mu1 is going to greater than mu2 like this. Okay, they are organized in the decreasing ones. So here it is going to be I greater than n. Whereas when we had a regular single player case, it was I not equals to I star, except for the optimal one, I'm summing over all. But here I'm only summing over all the arms which are after n. Okay. Now, is it possible? Now the question is, can the lower bound for this centralized case can be achieved in a decentralized setting? I want to see like if anybody has any thoughts on this aspect. So I'm now just going to give you an overview of what kind of algorithms are there. Just want to see if anybody has any thought on, like, do you even think that whatever the centralized bound that one can get for this multiplayer setup can be achieved in a distributed setup? Can anybody has any vague thoughts or just like feels yes, no, or at least want to make a wild guess? Okay, see, like maybe like you people are not able to like think, right, because it's a complex problem. Like you are talking about, okay, centralized, and can it be achieved totally in a distributed setup? Yeah, indeed, this problem is that's why complex, and lot of works have come recently, yeah, on this topic, and that too in very good conferences. So I'm just going to talk in a minute or so about different works that has come. So this is something called a Rorand algorithm, which, and this TDFC, which has, they kind of started this line of work along about 10 years back. And since then, some recent algorithms have come. Like mostly I'm going to talk about this. I'll just introduce the idea of this Rorand algorithm and talk about this musical chairs and this MC top algorithm. I'll just talk about some of our works on this talk as well. So what broadly we can say is the work in this on this topic can be broadly classified into two band of literature. One set of literature where the collisions are used as signals. I said that in a decentralized setting, collisions are unavoidable. If it is unavoidable, you better utilize them. Okay. So what this set of uh, papers do is they kind of use these collisions as somewhat signals and try to like kind of try some infer something like avoid playing that channel or something. Whereas this another set of work that has come very recently in the last and previous year, what they do is like if their collisions can always happen, why don't we leverage the collision to our advantage? Let's force, instead of avoiding collision, let's force them, and through this collision, let's do kind of some information exchange. Like anyway, like collision, we can treat it like a 0 1 bit, right? No collision 1 bit, collision 0. So this kind of collision itself can be kind of used as some bit information to exchange, and maybe this set of works try to come up with algorithm based on that idea. Okay, fine. Now in crux, when I go from single player to multiplayer, what is going to happen? Can all the players play, let's say, this single player algorithm itself, and can hope to do better in the multiplayer case? Like, I'm just asking the question. Okay, don't worry, you're in a distributed setting. Let all the player run their UCB version, like as if they are the only person in the network, and then run. What is going to happen? Do you think that's going to be a good idea? Anyone here? Anybody feels that why not just simply use the single player algorithms across all the players? Do you think that should give something? So that should not give anything reasonable, right? Because this is a homogeneous setting. Everybody is saying the channels in a similar way. So everybody want to, if you are going to use UCB, everybody want to go to the best channel. And then if everybody want to flood to the same channel, there is going to be always collision. So you are going to get nothing out of it. So what this yes, Pawan, that's what I'm saying. Like if everybody want to flock to the same channel, then basically even that's not going to happen, because you are always going to see collisions and you are not going to get any information. So maybe initially when you are exploring, you got some information, but now once you want to flock to the best one, everybody is doing that, so there is going to be only collisions. So this is going to be a very bad idea. So because of this, what the algorithms in this area does is somehow use this single player strategy, but somehow make sure that the players get orthogonalized. Okay, they want to kind of induce some orthogonalization by kind of making people to give less preference to the best one, or maybe like go to the other one. So here one algorithm that Rorand I mentioned, this was one of the early algorithm. What it basically did is every player is running their own UCB version, but everybody maintains his own rank in every round. So that is the rank for the user. User is going to assign a rank to himself, and he is going to play. First, he is going to rank the whatever based on his statistics. He is going to come up with a top n rank, and then he is going to play the RTth best arm in that. Okay, so he assigns a rank. Let's say he assigned himself rank 3. So then he's going to play the third best arm. And if a collision occurs, that player is going to reassign a new rank to himself out of the n ranks. And if that rank remains the same, he is going to continue to play that, and he is going to update his UCB link. So you see that the only thing that is now in the multiplayer thing is bringing is somehow they want to player to keep fighting for the same best term. Like you kind of randomize them so that they select one of the different arms on the top n arms and be content there. Like for me, it does not matter user is on which channel in the top n arms. As long as he's in one of the top n arms, that should be fine with me, right? And based on this thing, it has been showed that this algorithm is going to give you some regret, which is like n square and all. So this is optimal in terms of t, but not in terms of the other ones. But still, like they have shown some means to like how to randomize so that while playing UCB algorithm itself, players settle on the top n arms. And based on this idea itself, some modifications has been done, and some recent algorithm called the MC top M. Here, what they are going to do is, it is a small tweak to kind of this row and algorithm. Now, players are going to maintain a set of top n arms. Everybody is going to maintain the top n arms, and what they are going to do is, if they are not going to see a collision on a channel, they are going to get fixated on this, right? And this is a kind of things we also talked in a random hopping earlier. Like I select a channel, like I have a set of channels maintaining top n, and I will select one, let's say, and I don't see collision. I get fixated on that, and unless I see a collision on that, I continue to play on that arm, like unless. And I also keep updating the statistics. Either that channel moves out of my top m arms, top n arms, or like I see like I have not yet fixated, like I will keep select one of the arms from the set and play. So this is a small tweak to this Rorand algorithm, and we are going to get some improved regret bounds for that. And one more new entrant to this is called musical chairs. Like the previous two algorithms somehow built on the UCB algorithm itself. Like they were just like adding some scheme to UCB so that user orthogonalize. But this musical algorithm is not based on UCB at all. Here, and also the previous two algorithm assume like since they are using UCB, they kind of assume how many players are there. But this algorithm not using UCB, but it also assumes that I don't know the users. So what it does, it basically builds an algorithm based on two phases. One is called random hopping and another is called musical chairs. What is this random hopping doing? So this is like a very simple algorithm. It's naive, but fine. Like it is going to overcome the requirement that I have to use UCB indices all the time. And like I don't know the number of users also. So what it does, like it kinds of forces initially in the phase of random hopping, it forces all the players to play these arms selected uniformly at random. And once it is done, based for certain number of rounds, it computes based on the number of collisions. It kinds of computes how many users are there. So it's a kind of intuitive, right? If there are more collisions, maybe there are more users in the network. If there are less collision, possibly there are less numbers. And based on this random phase, whatever sample collected, it also finds the top n arms empirically. After that, what it does, it again goes for the musical chair phase. Musical chair phase is nothing but it's another random hopping phase. Now the random hopping is restricted to top n arms, which is computed from the previous hop. And if players select uniformly randomly from the top n, if they happen to see a collision, they will again go and select another arm uniformly selected random from top n in the next round. Otherwise, they will stick. So this is a simple algorithm. And what this algorithm says is like we are going to get a good regret provided I am able to set this T naught, the number of rounds in T naught appropriately. So for this, it makes an assumption that, okay, I somehow know the gap between the nth mean and the n plus 1. Suppose if you give me a lower bound, it says that I can set this T naught appropriately and I will get a regret, which is going to be constant with high probability. So like see, now I have come out of the UCB, like now I'm not looking at some log T bounds. What I'm looking is, will I eventually go to the optimal allocation in some good time? And this algorithm is guarantee that. But the drawback of that is, this algorithm is like, we don't like collisions in this wireless setting, right? Like it is forcing collisions, like to get a good estimates of number of users. That is a bad thing, and also it needs some knowledge about the lower bound. So they have a dynamic variant of this. I will not go into that because we are now. So if users are coming and going, there is a method like this algorithm can be adapted for that. Okay. So now I want to talk about this our work on the static tracking, which builds on this. Again, this algorithm, the whole purpose of this algorithm is to somehow get rid of lot of collisions that musical chairs is forcing. Okay. What we will do is this algorithm is now going to run in like three phases called as random hopping, sequential hopping, and tracking. Random hopping we already talked, like everybody selects channel uniformly and random. But once they select, the random hopping phase ends, right? The hope is, right, when the random phase ends, everybody is on a different channel with high probability. And then comes the sequential hopping where everybody goes through the channel sequentially, and now there is no collisions. See, this is where we are trying to avoid collisions in the network. Like quickly orthogonalize them, not necessarily on the best channels, but they're just orthogonal, and then make them go through sequentially. And then comes the tracking part. So this tracking part, like I will just give you a broad idea that what in tracking part is doing is once this sequential phase ends, like everybody tries to find what is their empirically best top arms, and in whatever the current arm, they want to go something above it. For example, let's say like user one is on channel two, user okay, this should be user three here. Uh, it should have been let's say user, okay, so this is correct. So let's say this is user 2 here, right? So what you want is user 1, according to him, this is the best channel, he want to go there, and user 2 is in the fourth best channel, he want to go to the third best channel, he want to go there. So everybody tries to go up as long as they don't see a collision. If they see a collision, like for example when both of them went up, they will see a collision here, they will come back. And to make this algorithm work, we have to introduce some reservation phase and all. I mean, for details, you can look into our paper. So again, based on the same setup that whatever the musical chair said, like if we also assume that I know this lower bound, we can come up bound our regret bound. So instead of looking into the regret bound, let's say that what is that we gain in our regret bound. We say that our regret bounds are going to be about 4 times better than musical chairs. So that is one aspect, like in fact, like we are doing better than the regret. Now what is good is like its collisions are going to be much lesser. Like what we show is it is like about 12.5k factors less than the musical chairs. Why is this gain? This is gain is basically coming because we have a sequential phase where people are learning the channels while being in orthogonal fashion. Okay. Again, we have a dynamic variant of this. What it does is like somehow, like if the number of players who are entering and leaving the network is some x, then this regret can be like a bounded like square root t. And this is what we call it as a dynamic tracking. What this algorithm we bring in the concept of sensing, like whenever a new player comes, right, you should not disturb the previous ones because previous ones may be in the tracking phase other. So it is going to do some sensing, and only when the channel is vacant, maybe it will take. Otherwise, it will keep quiet. And by just this bringing sensing, we are able to make the user enter and leave at any times. So this is one of the features required in dynamic network, right? User should be free to come and leave any times. If you restrict when the user can come and go, that could be problematic. But just by introducing the sensing, this can be done. So here are some experimental graphs which says that like the regret of MC is okay. So there is okay. Let's look into this. So the number of collisions in MC can be very high, whereas ours can be very less. And this is also the case where the dynamic setting, right? Like here the vertical bars denote when the players are leaving or entering. We see that like our algorithm is going to do much better than uh, the DMC, where DMC is the dynamic musical chairs. Okay, it is its regret of goes bad as soon as some entry or exit happens. Okay, so maybe in the now I talked about algorithm. Like as you see it, in all the previous algorithms I talked about, like kind of collisions are kind of used as like signals, right? Like okay, if I see a collision, maybe I will fall back, or if I see a collisions, maybe I will not stop, like maybe I will keep sensing or something. However, as I said earlier, these collisions can be used to our advantage by kind of using available channels itself instead of transmitting data on them. But maybe we can do kind of signaling by colliding in some particular fashion and by communicating 0 1 bits. Not going to go in details about this, but this will help user to kind of achieve kind of exchange some information, kind of do some kind of implicit coordination, not explicit, some implicit coordination. And as you see, like once there is some coordination comes, right, we should be able to do much better. But any kind of collision induced, they are like a basically lost slots, right? Because I'm not transmitting in data in that, and that should be counted as collisions. Sorry, regret. And in fact, this recent algorithms, and this DLE is our own algorithm, which shows that in fact one can control these collisions in a pretty well manner, and there won't be much regret loss because of this force collision. And in fact we will be able to achieve a regret bound, which is I said initially I asked this question, right? uh, can this lower bound be achieved? In fact, I mean, it is possible to achieve this lower bound by this implicit collisions. So those interested in this line of work, please take a look into this kind of new algorithms which propose like how to use or force this collision and control them in a particular fashion that even in the distributed setting, we should be able to achieve a regret that correspond to a centralized setting. Okay, now quickly move to the multiplayer setting. Let me pause for a minute and see, like I lost everybody else. Is there somebody still following me? Okay, Tony has a question. Yeah, good question, Tony. Like, yeah, definitely, you made a valid point. So far, what we assumed is the number of channels is going to be greater than number of users. And kind of we also motivated this kind of work for like IoT devices and ad hoc networks, right? Then you might be wondering here, I mean, why in reality, maybe the spectrum is very costly resource and it's scarce. Like I don't expect too many channels. Is this a valid model? Yes, you are pretty correct. Whenever this all these models are assuming that k is greater than 1, and that has been one of the limitations. But whatever the algorithm I said, tracking and all, if there are n k channels and there are more number users, let's say k is as you write like n is greater than k, at most only k users can be supported, right? Not all n users can be supported. So in that case, all we need to do is make sure that each of these users, at least one of them get one of the channels in the k, and whoever not getting channel, they have to be drop out of the system. There is no way I can accommodate them, right? So that is been a issue in some of these algorithms. Most of the algorithms work strictly under the case that a k greater than n. But what should happen is like there should be provision that like if there are more number of users than the number of channel, those extra users can't be accommodated, and they should get a signal that the network is full. I should better wait. And that in fact happens in our tracking algorithm. I didn't go into the details. Like in our initial random hopping phase, right? Our algorithm has a random hopping phase. Okay, let me go quickly there. So I said here our algorithm has a random hopping phase, right? Like for some reason, if the user don't get any collision free channels in this random hopping phase, he got an indication that he should better stay out of the system. Like system is full. I can't be accommodated now. So these kind of things happen with this kind of in the tracking algorithm. Unfortunately, this can't happen in the if you are going to use the UCB based algorithm. So like maybe you will continuously incur collision and you don't know whether everybody is selecting that. Just because of that it's happening, like everybody is flocking to the same channel, that is why collisions are happening. Or is it that the number of channels are not enough? So that is one distinction between the static tracking and the UC based algorithm. We can accommodate that case. So good point. Like there should be provision in the algorithm which tells which should indicate the users that full stay out for some time and try later. I hope that answers your question. And indeed, tracking is one algorithm that does that. Okay, I was mentioning that the allocation need to be done over time. That is, make allocation in time slot t. Right, like how these algorithms are designed, right? There's a random hopping phase, and after that, arms users are going to learn channels, and then they are going to take the one of the channels. Now, while the random phasing ends, right? If that time itself there are more number of users than the channels, the extra users had to leave, and whatever the remaining users, they have enough number of channels to get one each, and that is and if there are as many users as the number of channels, then that just giving one to each one of them is the best thing you can't do. You can't do anything better than that. So instead of looking at every time, you should be thinking like, okay, after the random phasing ends, something happens where everybody is told, okay, get out if there's no space. And subsequently, for everybody, there is enough space. See, like if there is too many users compared to the number of channels, right? So then the only best thing is like everybody, the out of n users, only k users can get one channels, like one channels, and one each of this k users get one channel, then your accumulated reward is already maximized, right? Like there's no loss, like everybody on everything. If you have k users and k channels, giving one channel to use user is the optimal thing. Fairness. Okay, good point. In the fairness, if you look into our this algorithm, right? Again, I'm going back to this algorithm. We say we have this sequential hopping phase. So algorithms are doing it in a round robin fashion. Like once the random hopping phase ends, the users go through sequentially. So everybody is seeing each channel almost like equal number of times because of this round robin fashion. So this already brings in fairness. Does that help, Tony? Okay, great. Uh, okay, so okay, I'm really overrunning time. Should have handed over to Sumit by this time now. I will just run through this uh, multiplayer setting for a heterogeneous case. Okay, now I want to move to the heterogeneous case where the number of each player can see potentially different gains on the channels. Sorry, what's happening? I should be maximizing this. Okay, there have been some works on this, and the again we can classify these works based on how these collisions are being used. Some works I have put like these are all again in the heterogeneous setting. There is a one paper called DUC before algorithm, and the D3. These are again built on the UCB idea, but they use signals as collisions as some kind of information. And there is also a recent paper called the Game of Thrones. You brings in some game theoretic concept based on like each user trying to maximize their own utility based on this idea, this work. But recently, just last year and last year, there has been some algorithms which are again going to use this collision as a communication means and try to come up with the optimal algorithms. All these algorithms here, right, like in this collision as signals, none of these algorithms are going to achieve the optimal algorithms. They are at best near optimal algorithms. Okay, but whereas using this collision, one able to obtain optimal algorithms. Okay, I want to quickly rush through this. Like this is one of the algorithms we developed called for the heterogeneous setting called ESC algorithm. What this ESC stands for: explore, signal, and exploit. So in the classical single player algorithm, there is only explore and exploit, right? But now in the multiplayer, there has to be some means like to talk to players. So that is what we are calling as bringing in this S term here. That is signal. You explore, and some kind like whatever you explore kind of convey to the other through signaling, and so that everybody has a kind of a common information, and then everybody jointly exploit. Okay. So in the signaling phase, like what we are saying is like users are going to communicate like whatever they kind of learned about the channel statistics, and there are different mechanisms that we have discussed in our paper called Bernoulli and packetized signaling. You may want, if those interested, can look into that. Now, fine. So this algorithm is shown to be have order regret like n square k log 1 plus beta. So beta is some positive quantity here. You see that this is not like a log t regret, it is a log to the power 1 plus beta. So in a way, like it's like a near optimal algorithm. But it is a lot simpler to implement. And the good thing about this, even though you are in a heterogeneous setting, this algorithm extends to dynamic setting. However, in the dynamic setting, one has to again make some necessary assumptions, like there should not be any arrival and departure in the exploitation phase. Sorry, this should have been exploration phase, like so that they don't disturb others while exploring. And we also don't allow simultaneous arrival and departure. They can be arriving and departing at some time, but not simultaneously. And what the modification we have to do to the ESC for the dynamic setting is we have to somehow make sure that people are aware when arrivals or departures are happening. So whenever a departure is happening, right, we are forced that the leaving user to make one collision with all and leave. So everybody is aware that one channel has now become vacant. And similarly, when a new arrival comes, he also want to like kind of collide with all the users to indicate that okay, somebody has entered the channel. By doing this, we can extend this ESC algorithm to the heterogeneous case, and we are able to show that this has a square root t regret. So now one remark I wanted to make here is like, see, like our algorithm here, even though it's good, empirically good, and extends naturally to the dynamic setting, it is still not optimal, right? Because of this log 1 plus beta. So there is a recent paper called based on this explore then commit ETC algorithm, not like our explore, signal, and exploit, which is like happening repeatedly. It achieves optimal regret whenever there is an optimal, sorry, the matching, the optimal matching is unique. Okay, I will just take two quick moments to explain the case about stable matching. I talked about stable matching, right? So far I was focusing on optimal matching. In the homogeneous case, stable matching don't make sense. Whereas in the heterogeneous setting, it makes sense because users are seeing different one, and they want to change from one channel to another. For this, we have this algorithm called DSOC. What is DSOC saying? Distributed, stable, orthogonal configuration. And this algorithm runs in two phases, basically random hopping and sequential master and channel switching. Just like instead of going into details, just look into this figure. After RH phase, everybody has this one shot, what is it is called a one hop switching blocks. This total time is divided into T. Further, we are kind of trying to build a signaling mechanism where everybody can tell whether they want to swap arms between them. So here we are, each OHS we are dividing into a master blocks of size K. So one master blocks correspond to one particular user, whoever is on that particular arm. And in each master block there is CT and CS. And the CTS CS is signals is what we are using to kind of tell. Like in CT, if a user collides with other user, it's kind of a indication for them, hey, do you want to change your channel with me? And if he agrees, the other user in the next channel also they collide. So that means they agreed. Okay, they are happy to change their change channels and they swap. So here is what happens. Like I mean, you can look into this different possible scenarios happen. Like it's not necessary that whenever a player makes a request, the other guy accepts it and allows the swap. It may it channels request may get accepted, it may be denied, and you are requesting for to take over a vacant channel. So this all happens, right? So what we show is in this case, like it is possible to, like our algorithm with all the signaling scheme is going to achieve this stable allocation in some finite round, and that too with probability one with some high probability. Like you can set delta to be whatever you want. Again, our algorithm signaling scheme in such a way that one can tweak it to even adapt to the dynamic setting where users can come and leave at any time. All we need to do is bring in some extra synchronization phase. What is the synchronization phase? So you remember that we have this block structures, right? When a new user comes, he need to know what is the starting point of this block. So that synchronization phase is required. And for that, what we'll do is when a player comes, he piggybacks on one of the users. Like he just looks which channel is transmitting. He stays that and see that when that user is going to become a master. Like one user is going to be master in each block, and based on that, he'll figure out in which frame he is. And with that simple modification, this extends to this dynamic setting. Okay, this is all about, like as I said, there is a plethora of papers come in this, and I have discussed few, but there are many other possible scenarios which I didn't discuss. And for those interested to pursue this, here is what some of the recent papers and some of the recent directions people are looking in this. So multiplayer bandit one is, like we assume that the collisions are observed, right? What happens if the collisions can't be observed or the collision feedback is not available? So that is all this in whatever the new IoT setting that happens to be one of the themes. Like uh, nodes don't sense, they simply transmit. So these two papers have come up in this. You can look into that. And other thing is we also for studies only stochastic case. What happens if the environment is not stochastic, right? Like rewards are generated in an arbitrary fashion. Even in that, like recently, just like last year, a paper has come and something is still under review. So those interested can look into that. Okay, these are like broad things that I covered. What's happening in this multiplayer bandit setup and how that will be useful to achieve optimal allocation and a stable allocation. So what are potential interesting problems here? You see that even this is many recent works have come in this, like people are still actively looking into these areas. So some of the potential challenging problems and interesting question to ask is like, what happens, like why is that one need to assume that when two players select a channel's collision happens, why can't the rates on that channel be shared? Maybe you can do a coding scheme or some interference suppression scheme so that both player get something instead of zero. Then in that case, like how to define what proportions they get and what is that observation they get, and how this reward split, what function of it is all valid questions. And if that is the case, how to, what kind of regret possible to achieve. Also, all the algorithms we had in the dynamic case, there's still a lot of improvement because they assume some kind of restrictions. User can't come now, then, or like they should only come in particular slots. How to remove all those? Other theoretical interesting questions of interest is like what will be a lower bound in the heterogeneous setting. Heterogeneous, as I said, is a very complicated thing. I mean, the clear lower bound is not known, and because of that, it's hard to say like whatever the optimal bounds we get are optimal or not. So what will be a lower bound, and then show like is there an algorithm which can achieve this. Okay, so and another thing, as I already mentioned, like most of the bounds derived here assume that the unique matching, optimal matching is unique, but there could be multiple optimal matchings also, right? Like how to do learning in that case. Okay, so these are some open problem. So I would like to thank some people here who worked with me, especially my PhD student, and these are two BTech students at IIT Bombay who worked on this ESC algorithm. Now they are graduated, they work in different company. And Sumitya and I have been collaborating on this for some time now. Yeah, and these are, I want to apply my funding. So here are some, whatever the earlier algorithms I was referring, right? All these are RORAN, TDS, Mega, MC. These are reference I've given. I am just flashing it so that in case you want to refer to them in future. So thank you. I would exceed a time by 5 minutes. If you have questions, I can take now.
So Manjesh, in the meantime, can you stop sharing so that I'll check
Yeah.
the slides?
Yeah. Okay. So Nikita Trivedi is asking how the other players will identify from the collisions whether the observed collision is from the arriving player or the departing player. Yes. So I mean we have to just make a simple uh, case here, like maybe like just like a distinguish whether the player who is departing he collides multiple times and the player who is arriving just one times. So we can just distinguish what we assumed in our when we derived our regret bound is like the arrivals, the departures are easy to handle. Like whenever departure happens, right, it has basically not disturbed the other player, whereas whereas um, whereas when your new player is coming into the picture, he is going to disturb. So we can just assume that the new arrival player is going to like maybe collide multiple times and the departing one time. That should be enough to distinguish. Yeah, I mean this distinction is not an issue. Like it's just like a protocol thing, like how you want to. These are like a pre-agreed thing. Like we can tell in users like how should they be behaving. Uh, okay. Any other questions?
Okay, so then Manjesh, I'll start then because
Okay.
they are a
I
bit.
am
Yeah, are you able to see my screen, my
not yet.
slides?
Not yet.
Not it.
Just a
Okay.
minute, Arpan. You want to just give some 1 or 2 minutes break while yes, it's been. I didn't notice like we went for almost 2 hours. Okay, maybe like yeah, Sumit, just wait a minute and get started.
Yeah, are my slides are visible?
Yeah, Sumit, I can see them now.
Okay, okay. I think we can start now because initial part will be some introduction, so it will take some time to get this one because uh, yeah. So good afternoon, everyone. I'm Sumit Darak. So to be in the beginning, I will just like to thank Arpan and Nadim for giving us the opportunity to present the tutorial at the COMSNET, and also thanks to Manjesh for setting up the problem nicely and also discussing the MAB architecture algorithms in detail. so that for me it will be easier to discuss the architecture part. So one of the reason why we decided to include the architecture parts in the algorithms is to first discuss the what are the practical challenges to bring these algorithms for a certain application, especially wireless physical layer. And second is when we develop the architectures for any algorithms, it also helps us to understand what are the precautions or what are the necessary things to be taken care into account while designing the algorithm so that it is practically implementable on the hardware. So that is the reason. So the aim of this talk, which is the 1 hour talk, is to discuss the how these simple MAB algorithms can be mapped on the hardware, and what are the challenges as if you are an algorithm designer, what are the challenges you need to take into account while designing your own algorithm so that it is feasible on the hardware. So the outline of the talk is that we'll discuss why there is a need of mapping the algorithms, MAB algorithms on the architecture, why they can't be run on the just a simple CPU. Then once we convince you that okay, there is a need of mapping the algorithms on the architecture, then we need to understand what are the available platforms which are available in the market or which are widely used to to map these algorithms on the architecture. So these are the platforms we usually call as a system on chip platform. There are a wide variety of platform, but overall the architecture more or less are identical. Then we'll discuss that mapping the algorithms on the architecture is not sufficient. When you map the algorithms on the architecture, you need to make sure that the architecture is reconfigurable, because, or in the simple words, it should be adaptive as per the environment, and it should be intelligent enough that it should learn from the environment, it should able to adapt or reconfigure itself. So how to design this reconfigurable and the intelligent architectures, especially for the MAB algorithms, we'll discuss. And once we introduce you to the entire flow of from getting the algorithms to the architecture mapping, and then making it as a reconfigurable and intelligent, we'll also discuss how the same flow can be used for the other more complex algorithm, for example deep learning algorithms or the wireless PHY, where you have a lot of signal processing blocks, and how to make the wireless PHY intelligent and the reconfigurable. So most of the work which I'm going to present today is done by the my student Sai Santosh, and we have made the source codes and the handouts available on the GitHub. So if you are interested, you feel free to look at those aspects. So the first challenge for me is to convince you that there is a need of mapping the algorithms to the architecture. Because as if you are an algorithm design, you might think why I need to, why there is a need of mapping the algorithms to the architecture, or why I should worry about the architecture. So let's start here. Suppose you are seeing some plot on the screen. You can see that on the x-axis you have the year, which indicates some 2008 to 2020, and on the y-axis you see that market in billion US dollar. And if you look at this link, it is seems like it is related to the some cloud computing market. And what you are seeing is that there is an exponential growth in the cloud computing market over the last 10 to 12 years. And as we know that this exponential growth is because of the significant large scale deployment of the IoT devices, and now this IoT devices has also reached our home through Alexa or Google Home. And all these IoT devices, we are told that these are very intelligent devices, but in the architecture level they are really dumb devices. Why? Because they usually only do the data collection task, and all the data processing happens at the cloud network. But the problem is the cloud resources are limited. We can't, the number of IoT devices are increasing. The amount of data which is being transmitted to the cloud is exponentially increasing, but we have the limited cloud resources. So there is a need to enable these devices to do the local data processing. Also, from the green and security aspects, we know that the data centers which are doing this cloud data processing or data storage are not green. There is a significant amount of electricity is needed to maintain this data center for the cooling and the other tasks. In addition, we need to take care of the data redundancy and quality of service, so that we need to replicate the data at the multiple location, so that the data access is available at all the time. And it is expected that the overall energy consumption will grow up to 20% of the global electricity of these data centers by 2025. So that is one of the major concern about how to maintain these data centers, as our growth of the IoT networks is exponentially increasing. If you are interested in the design, understanding this, how the data center works, there are a good tutorial videos are available by Google, Facebook, Microsoft, how they maintain their data centers and how they reduce their energy efficiency. So green is not one aspect. This another aspect is the security issues. So whenever the data goes outside your network or outside your home, there is always a security concerns are there, and especially last couple of years, we are hearing a lot of news about the how our data by say Alexa or Google Home is being used, or for some other purposes than our intended use. So and recently there was one more news that these are not only collecting the data, our voice data, but other data are also being collected by via three devices. So this is a major issue. Security issues are there, security and the privacy aspects are there, and this will be the issue whenever the data is transferred outside your network. This issue cannot be avoided unless we have a very stringent encryption and decryption protocols. So these are the certain aspects about the cloud computing approach, where your entire data processing happens at the cloud. So you need to take care of the cloud resources, which may end up having the higher latency, the green and the security aspects, and this has led to the uh, term which is called as the edge computing or the decentralized intelligence, where the aim is to move some of the computing at the cloud to the edge devices. So these edge devices can be at your sensor level devices or your gate level devices, or at the or certain can be at the cloud level. So there are multiple intermediate stages of computing are there, and the aim is to move this some of the decision making capability from the cloud to the edge devices. So this is the one of the aspects of the why we need to implement this decision making algorithms, which can be MAB algorithms or the reinforcement learning algorithms at the edge devices. As Manjesh has already discussed about the distributed wireless network and why we want to make the decision making decentralized instead of the centralized, because there are certain because it may not be feasible to have the centralized decision making in the large scale wireless network. In addition, same algorithms are widely used in the robotics or the ADAS, automatic driving assistance system, where some kind of intelligence is being deployed at the edge level, and we can't have the decision making at the cloud level because of the latency issues. Because the decision in case of the robotics on the ADAS application, the decision needs to, there are some latency constraints are there, which means the decision needs to be taken within certain time. So these are the motivation for moving the algorithms to the edge level, and that means we need to implement these algorithms at the edge platform. So if you have seen even in the 5G or the some discussion is happening at the for the 6G also, that there are particular application which demand the stringent latency constraint. And if you see in the 5G, you have the specific vertical called URL LLC, which is being considered for the applications which have a very tight latency constraint. And if you are following the 5G base station design protocol, there are multiple split up options are being developed for the 5G base station. And you will see that now in the 5G, there is a way to have a very tight integration between the physical layer and the MAC layer, which means the decision making algorithms, which are usually there in the MAC layer, there is a possibility of accelerating them using the hardware, which is normally used only for the physical layer. So this is another reason for developing the efficient architecture for this decision making algorithm. So that's the reason we are talking about. Instead of just implementing this decision making algorithm, which can be a bandit algorithm, reinforcement learning algorithm, or the small scale deep learning algorithm, only at the CPU level or at the cloud level, how to move them to the edge level and how to efficiently implement them on the edge platform. And that's why here we will be discussing about the algorithms to architecture mapping for this decision making algorithm. So if you have any doubt, any issue, if you need any clarification on why there is a need of algorithms to architecture mapping, feel free to ask in the chat window. I'll take the question as and when needed. Okay, so now I hope I have convinced you that okay, now we need to map these algorithms on the architecture. So now we need to understand what are the different types of platforms are available to map any algorithms on the architecture. And in the last 4 or 5 years, there has been significant a significant improvement in the available platforms and available capabilities to make the algorithms implementation easier. So to understand what do you mean by system on chip, what do you mean by this platform, we need to understand the term which is the system on chip. So if you are in the digital design or the architecture domain, we usually use the two type of terms, which is the system on chip and the system on board. And you will see that the last 3 to 4 years, people are talking about the system on chip quite widely. So system on board, which is you can see on the right hand side, is the simple PCB based system where you have the multiple chips communicating through the external interface. For example, you have some Bluetooth based device or Wi-Fi based device, then you have a one chip for the CPU and you will have the one chip for the say Wi-Fi and one chip for the Bluetooth. For example, if you see the existing your mobile phone, you will have the separate chip. So the aim is to move to the system on chip. So what do you mean by system on chip? Instead of having the multiple separate chip, how we can integrate all your functionality inside the single chip. For example, if we have the one chip, so I can have the CPU and I can have the Bluetooth on a single chip, so that the communication between the two chips is the internal to the chip instead of the external to the chip. And as I'll show you later, that the system on chip always will always give you the better performance than the system on board because the communication is internal and it is also better in terms of the security aspect. So to conclude, the SoC is a single system silicon chip that can be used to implement the functionality of the entire system rather than using the several different physical chips on the board. Okay, so what are the advantage of the SoC? Okay, so in case of the SoC, we can see that we get the very high performance compared to the system on board, because you can see that the propagation delays are internal inside the chip instead of the external to the chip, and that means the propagation delay will be much shorter. Also, the overall impedance will be lower, and this will also help us to reduce the power consumption. Another major issue is that whenever you want to drive the signal outside the chip, the overall voltage level required are the higher than the whenever you want to drive the signal inside the chip. So that means your over power consumption will be less, and the outside the chip you will have the paths on the PCB which will have the higher capacitance than the optimized path inside the SoC. So overall power consumption will be significantly less. Also, as you will see over the years, the device footprint is going smaller and smaller, and this is mainly because we are able to fit the large number of transistor on a smaller area. And also, when you have, instead of having the two chips, if you have a single chip, your total size will be significantly less. It also SoC also gives somewhat better reliability than the system on board, because your signal is now, you don't need to drive the signal outside your chip. Since the signal is inside your chip, you don't need to worry about the interference from the external world or the security issues, because it is very difficult to read the signal internal to the chip than the signal which is outside the chip. And overall fabrication cost is going down over the years because of the number of chips you need to fabricate, and especially these are being fabricated in the large numbers, usually the cost is low. So these are the lot of advantages which are there in the SoC, and in the last 10-15 years we have seen the significant penetration of the SoC in our day-to-day uses. But now things are changing. Now the expectations of the users are also changing, and if you are a designer, your expectations are also changing. For example, till last say 10-15 years, if you take the example of your mobile phone, what was our expectation? We wanted our mobile phones to have as many features as possible, and it should have a very good performance. It should able to support the different kind of video games with the additional GPU, and it should be able to have the good sufficient RAM, so that your video processing happens at a good rate. So these are our expectation from the industry, and in addition, what we wanted that our power and the cost should be as less as possible. For example, over the last 10-15 years, what we wanted is that our battery life of our mobile terminal should last as long as possible, and the cost of the mobile devices should go down as many as possible without compromising on your features available in the mobile phones. And if you see the mobile market or even laptop or any electronic market over the last 10-15 years, we were very fortunate that our VLSI industries or the relevant industries have addressed this problem efficiently. And we are getting the mobile phones with the state of the art features, and the cost, if you see, is not significant compared to the amount of features we are getting on the mobile phones. Also, the battery amount of the battery we have, and the total battery power is significantly larger compared to the 10 years back the mobile phones we have. So the conventional challenges of having the higher integration and the performance and the lower power and lower cost have been addressed by this VLSI and the relevant industry more efficiently. But now the expectations of the designer, you consumers and the designers are changing. So if you look at from the consumer perspective, we are expecting a more flexible hardware, or we are expecting a more flexible device. For instance, when we switch from the 3G to 4G, we all know that we had to change the mobile phones, and the same thing is going to happen when we are going to switch from 4G to 5G. But you might have noticed that when we have the different variations of the 3G, like 3G, 3.1G or 3.5G, or inside even in the LTE, we had the different upgradation, but we didn't need to change the mobile phones. Why this was happening? Because the smaller changes were happening at the software level, and the software upgradation was quite easy. But when you go from the 3G to 4G or 4G to 5G, you need to do the upgradation at the hardware level. And the existing hardware, which is a ASIC based or the SoC based hardware, it is not reconfigurable, or it is not flexible. But what consumers are expecting from the industry is to provide us the flexible hardware, so that we don't need to change the mobile phones from going from the one generation to the another generation. Or even if you see in the case of the LTE, there are two versions of the LTE. In some country, you have one version of the LTE. In another country, you have another version of LTE. And the same hardware 4G phone which support one version was not supporting the another version. So you can have and what was the major limitation is that you have the hardware which is not flexible enough. Another issue, if you see, like migrating from the 4G to 5G is taking time, especially in India, because you can see that we have invested good enough infrastructure on the 4G base station, and changing from 4G to 5G, for example, upgrading the base station, you need to replace the entire hardware, because hardware which was used is not flexible. So the aim, the even from the industry service operator, they are requesting for the more flexible uh, architectures, or more flexible at the hardware level. Flexibility of the software level is more or less has been sorted out, but the flexibility of the hardware level is a big challenge. Second problem is the scalability, and this is the problem if you are a designer. For example, you are a designer, or you are a digital designer or mobile designer, and suppose that you are working on the mobile phone design. Say that you are designing the two range of mobile. One is the low level mobile with the limited features, and one is the high end mobile phone. Now, as a designer, if your company tells that for the say low level designer, you are going to use say this one processor with this architecture, and for the high level end, you are going to use this processor with this architecture. So if you are a designer, then what you need to do, you need to study the architecture for the low level processor, and you need to study the architecture for the high end mobile phone, and you need to adapt your code for the low end separately and for high end separately. That means you need to study the architectures of the multiple processors, and you need to get the expertise on this. And designers are really frustrated with this one, and there is a lot of demand from the designer that we want a hardware which is scalable. What do you mean by scalable here? That means the base architecture should remain the same, but when I map it to the low end mobile phone, or when I mapped it to the high end mobile phone, only the number of features are changing. For example, for low end mobile phone, I may not use the GPU, I can use the 2-core processor, but the processor architecture is same. And when I go for the high end mobile phone, I'll use the same architecture, but instead of using the 2-core, I'll use the quad core, or I'll use the octa core. I'll add the GPU or additional co-processor, but the overall architecture I don't need to learn, or my code can work on the both. At least if it is working on high end, it will work on the low end. And this is designing the something on the SoC is again hardware is always a challenging problem. So there is a lot of demand from the designer to design a scalable architecture, and this has led to the significant change in the architecture, or significant penetration of different approaches on how to make this SoC architecture scalable. And it's a challenging problem, because designing the some architecture which is scalable as well as flexible at the hardware level is not that easy, and that's what is the current major problems which industry is trying to solve. So I'm going to give you the some architectures which have been evolved over the last say 10 to 20 years, and how these architectures, and what are the reasons of moving from one architecture to another architecture. For example, in the simplest one, you have a single processor where you may have the multiple cores, say quad core, dual core, or octa core in a single processor. But you all know that if you want to implement any algorithms on the processor, it is a sequential process, so it takes the execution time is significantly large. And that's the reason, because to improve the execution time, this processor is augmented with the additional features like co-processor, or the floating point operations, or the GPU to improve the performance. So if you see in the mobile phones today, you have the processor which is the multiple cores, but in addition you have the additional co-processor or the GPU to accelerate the particular task. And then for the big system, for example, if you see the base stations or the large scale system, along with the processor, you also have the big ASIC based system, which will help you, the processor, to accelerate the large processing task. For example, FFT operation, which is a very common operation in the mobile devices, or the FIR filtering operation, or the matrix multiplication, matrix inversion operation, which are the very computationally intensive operation. It will be difficult to implement them on the processor because of the latency constraint, and that's why these are being accelerated over the dedicated hardware. So this is the ASIC system, which is the application specific integrated circuit. And in the conventional way, we followed the two chip system, where you have the processor and the ASICs, which are connected via external link. And then over the years, people have also explored replacing the ASIC with the FPGA. So here the FPGA stand for field programmable gate array, and it is a field programmable. So the discussion I was having in the previous slide regarding the flexibility. So to enable the flexibility, most of the companies are planning to replace this ASIC with the FPGA whenever there is a need for the flexibility. So these are the external multi-chip solution, and these are not a really SoC. So then, if you see around 2011 to 13, people came up with the SoC-based system where you have the processor as well as the hardware, which is the ASIC or FPGA, integrated on the same silicon. And what will happen, instead of having these external links, you have everything communication between the processor and the hardware happens at the internal level, and you will get the better performance. So this is the you can say that the SoC architecture, and people also call this as a heterogeneous SoC. Why? Because you have the two kind of system. One is your sequential operation based processor, which is your power PC processor from the IBM, and then you have the hardware, which is the ASIC and the FPGA. So where you can do the operations in parallel. So you have these two different kind of circuits which are implemented on the single silicon, and this is, people call it as a heterogeneous SoC. Then so Xilinx came up with the next version of this architecture, because when they see that when you move from here to here, you got the significant improvement in the performance, and then the choice was available to see the best processor available in the market, and that they came up with this Zinc architecture, where you have the ARM processors, which are the state of the art processor, implemented along with your programmable logic, which usually people call it as a FPGA. And here I have shown it here is a dual core processor, but there are various versions of dual core, single core, or quad core processor to get the desired functionality. So this is called as a AP SoC. So what is the AP SoC? This is the all programmable SoC, means everything is programmable. So if you see that here, if you use the ASIC is not programmable. ASIC is application specific integrated circuit. So that means it is, once you design some algorithm, it will run only that algorithm. But in case of the FPGA, it is a field programmable gate array. So even if you deliver the product to the customer, you can remotely configure the hardware to perform some other task. For example, if you implement the 2048 FFT in case of the LTE, and now for the 5G you need a 4096 FFT, you can do that operation you can do that hardware configuration remotely in case of the FPGA, but this is not possible in case of the ASIC. In case of the ASIC, you need to replace the entire chip. In case of the FPGA, you just need to replace the algorithms which is being implemented. So this is called as the AP SoC, where everything is programmable. Your ARM processor is programmable, that is the software programmability. Your hardware FPGA is programmable, and how they communicate between each other is also programmable. That is the AXI interface is used. And in the last 5 years, they have extended this architecture, which is called as the MP SoC, that is multi-processor system on chip. And what is this MP SoC? You have the ARM quad core ARM processor, which was there here also, but you also have now the real time processor. So you can see that you have the dual core real time processor. In addition, you have the GPU, which is implemented inside the same chip. In addition, you have the FPGA. So you can see that everything which you need to implement any complex system is there, integrated on a single chip on this SoC. And this is not so these are the evolution I'm just showing, which are there from the Xilinx one, but there are other companies. For example, Intel also acquired the Altera, and they also have the similar kind of architecture, where they have the processor as well as the FPGA on a single chip. Similarly, there are other devices, like for example ST Microelectronics. They have the AI devices, where you have the along with the ARM processor, they have the dedicated accelerator unit inside the single chip. So depending upon the type of operation, if you want to implement at the gateway level, or at the controller level, or at the sensor level, you need to choose between the SoC architecture. Similarly, from the NVIDIA also, they have recently launched the architecture, where the concept is same. You have the multi-core processors with some real-time processors, GPU integrated on a single chip. And in the couple of years, especially if you are interested in the wireless domain, Xilinx has launched the state-of-the-art platform, which is the RF SoC. So in addition to this MP-SoC, you can see that RF-SoC also has the digital front end. For wireless communication, whenever you want to transmit the data over the air, you need a multiple ADCs, digital up converter, digital down converter. Until now, this used to be developed as a separate system, because you have the other analog components on this in this digital front end and the analog front end. But now in the RF SoC, in addition to your MP SoC, you have the ADC, DAC, along with the dedicated hardware units. For example, in case of the 5G, you need a LDPC encoder and decoder for the data channels. And implementing this LDPC is always a challenging task. So they have dedicated silicon, which is provided on the same chip, so that you don't need to implement it as a separate unit. So there are dedicated units which are being developed only for the wireless communication required. So you can see that there is a significant progress is happening on the edge devices, and as a designer, you don't want to learn the architectures of uh, the all these things. So what you want is that architecture to be scalable, and that's why these devices are getting more and more popular, because you can see that if you learn the architecture about this one is almost same, because you just have the additional processing unit, and from here to here you can see that you just have the additional RF unit. So if you learn about the architecture of any one of them, you can move to any other architecture, and this we call it as a scalable architecture. And you can see that term heterogeneous all programmable SoC being used for the these edge devices, and depending upon the requirement of your edge devices, whether you want to implement at the sensor level or at the gate level or at the fog level or at the cloud level, different architectures are being used. So what I am going to discuss is now we have understand that there is a need of implementing the multi-bandit algorithms or decision making algorithms on the hardware. We also discuss about the different architectures which are available to us. Now we need to discuss what are the challenges available are there for implementing the existing algorithms to be implemented on this SoC, and what are the precautions needs to be taken while developing the algorithm. Okay, so before I move on to the bandit algorithms implementation, I'll just wait for half a minute, and I'll see if you have any question or any clarification you need on these aspects. So if you have any question or if you have any query, you feel free to ask in the chat window. Okay, so if there is no question, let's move ahead. And now we'll come back to the bandit algorithms, and we'll discuss how to map these bandit algorithms on the SoC architecture. And we'll start with the simple SoC algorithms. Okay, I see. Okay. Yeah, so we will start with the basic UCB algorithm. As we know that in the UCB algorithms, in the case of the single player bandit, the aim of the UCB algorithm is to find out the optimal arm and select the optimal arm as many times as possible. So assuming that we have the k arms in case of the UCB, and assuming that our horizon size is n, so we are going to sample the arms n capital N number of times, and assuming that we select the arm selected in the time slot n is the IN. And when you select the arm in the time slot n, which is the IN, you get the reward, which is the RN. So as explained by the Manjesh, what we do in every time slot, we select the arm, we get the reward, and we update our parameters, which is the total cumulative reward and the total number of times the arm has been selected. For example, X is the total cumulative reward on the arm K till time N. What we'll do whenever that arm is selected, we'll add the corresponding reward to that particular value. and whenever the arm is selected, we increment the value of capital T, which indicate the number of times the arm K has been selected till time slot n. So you can see that this is usually step 1, where we need to do the parameter update in every time slot. Then once we do the parameter update, what we do in the UCB algorithm, in the beginning, since you have not selected any arm once, you need to select the each arm once in the first K time slot. So that's what happens in the first K time slot. Each arm has been selected once. Then in the subsequent time slot, what you need to do, you need to find out the quality factor or UCB index in every time slot. And as discussed before, this quality index is a very simple term which consists of the two factors. One is the exploration factor, and the second is the this is the exploitation factor, and this is the exploration factor, where alpha is your exploration coefficient. So in every time slot, you need to look at the quality factor calculation. And then once you find out the quality factor for every all the arms which are there, all the active arms which are there, you will select the arm which has the highest quality factor. So you can see that there are very simple steps. Step 1 is the parameter update, which is the X and T update. Step 2 is the quality factor calculation for all the arms, and the step 3 is the arm selection. So these are the 3 steps which are there in case of the implementation of the UCB algorithm. Now, UCB is just a one algorithm, but similar to the UCB, there are the different variations of the UCB. For example, UCB-V, which is this algorithm, then UCB-T, which is this algorithm. On all these algorithms vary depending upon how you calculate your quality factors. The complexity of the quality factor calculation varies depending upon your algorithm, and there is a small variation in the performance of this algorithm. So why I'm talking about the UCB-V and UCB-T, I just want to point you out how the quality factor calculation and how it affects your complexity when you implement the same on the hardware. So assuming that you have the good enough understanding about the UCB algorithm, now the first thing is how to implement this on the hardware. Okay, so as we have discussed, we have the hardware which we take this simple hardware. We have the ARM processor and the programmable logic, which is the FPGA, which is there. So the way you implement in the Python or on the CPU, you can similarly write a C code or the Python code and implement algorithms on the software part, which is the PS processing system on the hardware. So if you look at this one, I have used the ARM processor here, and I implement the UCB algorithm here. I ignore the FPGA part. I don't use that one. I implement only in the programmable PS part, like ARM processor part of the algorithm. So you can see that what are the advantage of implementing the algorithms on the only the ARM part and ignoring the FPGA part. The first is the flexibility. For example, by changing the C code, I can easily move from the UCB to UCB-V or UCB-T algorithm. It's just a matter of changing the C code, and it can be done remotely also. That's not a challenge there. Then the upgradability. For example, right now I have the UCB algorithm, but in the future, my customer want the better algorithm or some more complex algorithm, say Thompson sampling algorithm or KL-UCB algorithm. I can do the upgradability in the real time, and that's what happening when you have the different upgradation in the 4G. You are doing the upgradation at the software level and not at the hardware level. But the problem is the latency of algorithm implementation on the processor is very high. For example, if you want to implement the algorithms on the processor part, it will be a sequential algorithm. For example, your C code is converted into the set of instruction, and it will be executed in the sequential fashion. So your algorithm latency is very high, and this is not acceptable in the recent application where you want the latency to meet the desired latency constraint of the application. And that's where you are you need to you need to divide your algorithms between the hardware and the software. Here the processor is your software, and this is the hardware part, and you need to divide your algorithm such that you get the desired latency constraint. So one approach is that what I do, I implement the algorithms I implemented the algorithm in this one of the fashion. Okay, there are multiple ways you can implement the algorithm, but this is the one of the fashion where I have implemented the steps, 3 steps, all in the FPGA. So you can see that the step 1 of the parameter update I have implemented on the FPGA part. then the quality factor calculations I have implemented on the FPGA part, and then the ARM selection I have implemented on the FPGA part. So this is the basic implementation of the UCP algorithms with the set k is equal to 2 arms on the SoC, which consists of the ARM processor and the FPGA. ARM processor does a very minimal task of the parameter update or the feedback updation. That is, the task is done by the ARM processor, and the rest is happening in the FPGA. Again, this is not a one approach. I can come up with a multiple way of implementing, having some part in the ARM processor, some part in the FPGA, depending upon the latency constraints which are available to me. So this is the one approach, and why how I have came up with this approach, and this is based upon the hardware software co-design. So what do you mean by hardware software co-design? Now I have been given this algorithm which consists of the multiple blocks operating here, and I need to decide which part of the algorithm will be implemented on the ARM processor, which is the processing system, and which part on the will be implemented in the hardware. And this is done by the profiling approaches, where you move around the blocks between the PS and the PL, and then you come up with the particular configuration which will meet your area requirement as well as the latency requirement. So there are different tools are available, but to understand, to come up with the better architecture, you should have a very good knowledge about the algorithm part and how the algorithm is implemented. For example, if the algorithm is doing the parallel processing, it is always good to implement in the FPGA. If, for example, if you go back to the previous UCB example, in each time slot, you are calculating the quality factor for every arm. Now, this quality factor calculation you can do it in parallel. So that part should be implemented in the FPGA instead of implementing in the processor, because if you implement the same in the processor, it will take a long time. So you need to understand the algorithm, and based upon that, you need to come up with the configuration which will give you the best possible trade-off between the area and the latency. Okay, so I have implemented this architecture, so everything is working fine. But you can see that I have the limited flexibility. What do you mean by limited flexibility here? Here you can see that my number of arms are limited to k, only 2. So if you want to change the number of arms to say more than 2, suppose that sometimes in the environment I have 4 channels available, sometimes I have 5 channels available, sometimes I have 2 channels available. But this algorithm, this architecture is implemented only for the 2 arms. So this is not will not be suitable for those environmental setting. Another issue with this algorithm is that, with this implementation, is that right now it is only giving me the UCB implementation, but you will see that in the practical scenario, depending upon the environment, UCB may not give the better performance. Sometimes for a given environment, your Thomson will perform better, or KLUCB will perform better, or UCB variation, UCB V, UCB T may perform better. So you need to provide the flexibility to the hardware, so that the hardware will be able to switch between the algorithms, and also it will be able to switch between the number of arms. Also, in some cases, your application scenario also changes. For example, here my aim is to find out select the optimal arms as many times as possible. But in some cases, it may happen that I want to implement the pure exploration based algorithm, where my aim is that I need to find out, I need to quickly find out which is the best arm, and then I need to give it to the my physical layer, or my wherever my application is. So you need to have the flexibility where your hardware should be adaptable, and this is where this FPGA comes a significant role to make your hardware flexible. For example, in case of the here, you can see that I have come up with the, I'm discussing the same algorithm which has the multiple processing part. And suppose that after doing a lot of hardware software code design, I've selected the F2 and F4 to be implemented on the hardware. And why I have selected? Maybe because they are more can be implemented efficiently on the hardware in parallel. And the second is that I may not be sure what should be the functionality of the F2. It may need to be changed depending upon the environment. For example, if you come back to the wireless physical layer, I may not be aware of, may not be sure what should be my FFT length, or I may have to switch between the different filtering parameters depending upon the environment given to me. So I'm not sure about the what is the exact configuration of the F2 and F4, or I may have the multiple option. So these are the things we need to move to the hardware, especially if we are using the FPGA, and we need to make them the reconfigurable via dynamic partial reconfiguration capability of the FPGA. And that's the reason the FPGAs are getting more and more popular, because you need, now the applications are demanding flexibility as well as scalability in addition to your performance and the power requirement. Okay, FPGA, no matter they are consuming more power and more cost, but over the time, with the more over the time, that is going to go down. But now the applications are more or less demanding more focus on the flexibility as well as the scalability. So with this feature, you can see that I can come up with the architecture. Here you can see that these are all are called as a reconfigurable part. So I can enable and disable these parts in the real time remotely. So you can see that now my architecture will be able to change between the number of arms. I'm able to switch. I can, if I need only 2 arms, I can have this one. If I need 3 arms, I can enable this section. If I need 4 arms, I can enable this section. So I have the better flexibility at the hardware level. Second is that it is just not the flexibility at the number of arms. I'll be able to change the number of type of the algorithms also. So depending upon the environment, I'll be able to say change between the UCB, UCBV and UCBT depending upon the my environment in the real time. Okay, and I don't need to implement all these algorithms. So you can see in case of the area requirement, I'm using only this area. I don't need to implement the UCB, UCBV and UCBT in parallel. At a time, only I need to implement one of the algorithm, and this will give me the significant improvement in the area requirement as well as the power requirement. And this we call it as a reconfigurable architecture. Why it is called as a reconfigurable architecture? Because in the hardware part is reconfigurable, where I'll be able to switch between the algorithms as well as the number of arms. So the advantage with this reconfigurable architectures is that I get a low power consumption, because I don't need to implement 3 algorithms in parallel. I can get the significant lower power consumption. Also, since my area requirement is less, I can move to the smaller or the cheaper area or cheaper FPGA compared to the complex FPGA. And then the feature richness. For example, right now I have delivered to the customer that I have this algorithm, I have this architecture which have the UCBV, UCBT. Suppose that you came up with the new algorithms in the future, I don't need to recall my product. I can reconfigure the same hardware through the remotely, where I just need to add the new algorithm in this section, and it can be done remotely without bringing your product back to your lab. So this is called as the feature richness and upgradability, which can be possible using this reconfigurable architecture proposed here. So if you look at the some result part, you can see that suppose that I'm considering the multi-arm-bandit setting with the 4 machines, and if you compare the total execution time when I implement the algorithm only in the software, and then when I implement the algorithm only in the hardware, and you can see that if you implement the algorithms in the hardware, you get the significant improvement in the your execution time, because you are implementing the algorithms, you are exploiting the parallelism in the architectures. Especially in case of the UCB, you can implement the algorithms by using the by quality factor calculations can be parallelized compared to the sequential calculation. In case of the processor, you can get the significant improvement in latency, and you can see that as the number of arms increases, your improvement here compared to the hardware is significantly you are getting the significant improvement in the latency, and that's what the applications are demanding. And this is I have shown with the 4 arms, but in the real scenario you will have at least significantly large number of arms, and you can see that the significant improvement in the gain can achieve when the number of arms are increasing. So this is only the latency. What about the resource utilization? You can see that when the if you implement the algorithms via reconfigurable architecture, or the other option is that I implement the architecture via using the Velcro approach, where I implement all the algorithms in parallel. And you can easily see that by using the reconfigurable architecture, you can get the significant improvement in the lookup table, flip-flop or DSP, which is the hardware multipliers available in the FPGA. You can get the significant improvement. So the reconfigurable architecture not only gives you the using the hardware not only gives you the improvement in the latency, also by using the reconfigurable features of the FPGA, you get the significant improvement in the area requirement. So hardware software co-design and the DPR, that is the dynamic partial reconfiguration, leads to the huge saving in the resources. And this is the case where we have shown it with the only 3 algorithms and the 4 arms. But as you know, the number of algorithms increases or the number of arms increases, there will be a significant improvement in the saving. Now, another advantage of using the hardware over the software based design is the word length. So if you use the hardware only, if you use the ARM processor, you know that your word length is always a power of always a multiple of 8 or 8, 16 or 32 and so on. But if you use the in case of the hardware, your word length can be any value. It is not restricted to the multiple of 8, and this is how the hardware works. So you have the freedom to choose the appropriate word length so that you can further reduce the your area requirement. For example, I'm showing you the effect on the functionality for a given statistics for the different word length. So you can see that I have here selected the UCB algorithm with the 3 word lengths. One is the floating point implementation, which we usually do it in Python, MATLAB, or the processor. Or the second is the UCB with the 27 bits and the UCB algorithm with the 11 bits. And you can see that even if I reduce the number of bits from 32, which is floating point, to 11 bits, you can see that the overall performance remains the same. Okay. This is for the particular scenario. In some cases, it may get affected at the 11 bits. It may not work out. So, but what here we want to highlight that by changing the word length, you can get the similar functionality, but what you will get is that you will get the significant improvement in your area requirement. So here you can see that I have reduced my word length requirement from 32 to 11 bits. Overall functionality will remain the same with the small degradation in the number of times the arm has been the optimal arm has been selected. But you can see that the overall area requirement, resource utilization, has significantly gone down. So this blue color is my resource utilization when I use the floating point implementation, and this yellow color is the resource utilization when I use my 11 bits implementation. You can see I didn't compromise that much on the functionality, but I have got a significant improvement in my resource utilization. And you can see that I'm not using the DSP units, which are the hardware multipliers available inside the FPGA. I'm not at all using them. And what is the advantage? In addition to the area, you can get the significant improvement in the power consumption, or instead of using the larger FPGA, you can go to the smaller FPGA so that you can get the improvement in you can do the cost saving. Okay, so the hardware software co-design with the appropriate word length and the DPR leads to the huge saving in the resources, and this savings will increases as you scale your algorithm for the larger number of arms or the more number of algorithm. So these are the things which are there while implementing the algorithms on the hardware. Okay, so what we discuss is that we taken the example of the simple UCB algorithms, and we discuss that how these algorithms will be implemented on needs to be implemented on the hardware. And we also discussed the effect on the functionality, word length, and the resource utilization on the hardware. Then the problem here is that how I'll choose the algorithm. Like for example, I have the now I have the option of choosing the UCB algorithm, UCB-V algorithm, UCB-T algorithm, but which algorithm to choose? So I need an intelligence for that. Okay, or depending upon the environment, which word length to choose? I need some intelligence for that. Or recently you will see that there are algorithms in the bandit family, which is sleeping bandit or sparse bandit, where you also need to select the number of arms to be searched or to be explored dynamically. So how to select that one? So you need some intelligence there to make your algorithm to make or exploit the reconfigurable architectures. Okay, and this we call it as a intelligent and the reconfigurable architectures, where in addition to have the reconfigurability is not just sufficient. In addition to have the reconfigurability, you need an intelligence to exploit that reconfigurability, and this intelligence is based upon the you need to interact with the environment. You need to look at the what kind of environment is there, and based upon that you need to select the appropriate algorithm. And even in the bandit family, there is a very limited work has been done in this domain, like how to select the algorithm for the particular scenario. For example, in case of the UCB, we have seen that all the UCB3 variations, they work differently depending upon the environment. Or in case of the some environment, in some statistics are Markovian, sometimes the statistics are IID. All these algorithms are based upon the assumption that your statistics are follow the particular pattern. But when you implement in the real environment, you don't know which statistics, which channels are following which statistics. So you need to learn that, and you need to appropriate or reconfigure your architecture accordingly. Furthermore, for example, if you take the example of the Thompson sampling, you have seen that the Thompson sampling has a different variation depending upon the distribution. So even the one algorithm may have the different variation depending upon the underlying distribution. So you need to have the intelligence, you need to have some kind of algorithm which will be able to explore among the options available because of the reconfigurable architecture, and will be able to identify this one. So from theoretical perspective also, very limited work has been done in this domain, and from the implementation perspective also, most of the algorithms are which we have implemented are the empirical algorithm. Okay, so this is the challenges on the designing the intelligent and the reconfigure algorithms, and we have discussed about the particular case of the UCB. What about the practical usefulness? So we have also developed the complete transmitter and the receiver physical layer, where what we did, we implemented the OFDM based transmitter, OFDM based receiver, and we used the multi-ambient algorithms to select the appropriate channel as well as the appropriate modulation scheme. So we have done this recently. This work has been done with the limited configuration support. So you can see that here I have the which is the my algorithm part, which we have discussed just now. In addition, we have implemented the complete transmitter file, which has the channel coding, data modulation, resource mapping, waveform like OFDM modulation, and then the preamble addition for the easier synchronization. Then you have the wireless channel here. You can have the multiple wireless channel, and by using the multiple wireless channel, you can sorry. So okay, just give me 1 minute. Yeah. Yeah, by using the multi-arm bandit algorithm, this multi-arm bandit algorithm is able to decide. You need to select the channel among the available channel, as well as the modulation scheme for the wireless transmitter, and the aim is to increase you increase your word length. So here you can see that uh, here you can see that everything is working in the real time. There are some latency constraint, and the aim is to how we can integrate the learning part with the real time, with the physical layer in the real time. So after we also have the demo working on that. You can look at the video available. So what we compare is that we compare the same parameters which we do in the bandit setup, but we have modified into the wireless fire parameter. For example, here we are comparing the number of error bits. So what is the number of error bits? Suppose we are transmitting 20,000 bits, and we are using the three different approaches. For example, one is the oracle approach, where we are selecting the we know which is the best channel, and we know the what is the best modulation scheme for that channel, and we are selecting this. So that is the oracle, that is the best one can do. Then second policy is the random policy. So random policy is that you select your channel randomly. And the third is the proposed UCB based policy, where based upon the UCB, UCBV, and UCBT, you select the appropriate algorithms, and then you for a given channel, based upon the signal to noise ratio, you choose the appropriate modulation scheme. And you can see that overall we perform much better than the random selection policy, and that is expected. And the performance is slightly worse than the oracle policy, which knows all the details about the channel. So that is the that indicates that by using the intelligence, you will be able to get the better performance even in the real network. Then we also discuss, suppose that we have a good channel based channel selection policy. How about the adapting your modulation scheme? For example, you can have a very good channel selection policy, but you fix your modulation scheme. For example, here I'm selecting the only the 16 com modulation. Then in another case, I'm selecting only the QPSK, or in the third case, I'm adapting my modulation scheme based upon my channel signal to noise ratio. And this is what it is being done in the LTE and the 5G, where based upon the MCS protocol, you adapt your modulation and the channel coding based upon your feedback you get. But here the feedback is here we are applying the same concept in the distributed at the user level. So here you can see that overall, when if I use only the 16 com, which performs very well in the good channel which has a very high SNR, you will get the better performance. But you can't use 16 com all the time. You need to if you use the 16 com for the poor channel, you will get the very poor bit error rate. If you use the QPSK, of course you will get a very good bit error rate, and that is the best you can achieve among the two. And in the proposed one, we were selecting the modulation scheme based upon the channel SNR, and you can see that the overall we are doing the much better than the COM base, but slightly poorer than the QPSK, and that is expected because we'll need to learn the channel SNR, and that it takes some time to learn the channel SNR, and that where it may happen that for some good channel we are selecting QPSK, or some bad channel we are selecting COM, and that's where the error performance slightly poor. But what is the advantage is the throughput. So overall throughput, if you see, in case of the QPSK, you are going to get the less throughput because you are transmitting fewer number of bits in a given time. While in case of the 16 com, you should ideally get the good throughputs whenever the channels are good, but you will need to do the transmission multiple number of times because you will get your error rate is very high. But in the proposed case, since we are identifying the channel, we are learning the channel, and we are adapting our channel selection and the modulation scheme depending upon the SNR. What we'll see that whenever the channels are bad, we'll switch to the QPSK, and we'll get the performance and the number of retransmission almost similar to the QPSK. But when the channel is bad, okay, when the channels are really good, so in that case, what will happen when the channels are really good? In that case, you will get the significant. You will be switched to the COM, and you will get the significant improvement in performance. Okay, so that's why by using the by using the multi-arm bandit algorithm, by adapting your modulation scheme and the your channel selection, you get the significant improvement in performance. So I'm in the last part of my talk where
Sumit, this is
yeah,
Nadeem.
yeah,
We are already 15 minutes past one. Can you wrap up in the next
just
couple of
5
minutes?
minutes. Yeah,
Couple of minutes, please.
Okay. So what are the major challenges in the algorithm is that we have taken the examples of the UCB algorithm, which is a very simple algorithm. But you will see that most of the algorithms which are used in the hardware, which are used in the bandit algorithm, most of them are the optimization based. And usually the ML people, they love optimization routine and they think it's very simple, but in reality, mapping this on the hardware is very difficult. And one case which we have already highlighted by the Manjesh, that the KLUCB algorithm is not at all synthesizable in the hardware, because in case of the KLUCB algorithm, you need to search for this Q part, which is for bit over the 0 to 1, and you have the infinite number of values, so it is not at all synthesizable. Then if you go further, other algorithm like Thompson sampling and the base UCB algorithm, they are mostly based upon the beta function, which are not at all synthesizable. And as a designer, we are happy because we get the challenge to work on this algorithm to how to map them on the hardware. So if you are working on the algorithms, you need to look at the how to design the algorithms so that they are at least feasible on the hardware or reusable usable in the hardware. All the you will see that there are multiple variations of the bandit algorithm, multiplay bandit, subset selection algorithm, which is again one of the major application in the wireless communication networks, pure exploration one. There are a lot of algorithms are being proposed, but most of them are not synthesizable. And this is the important thing we need to take into the algorithm. We need to take into account. And if you are working on the algorithm design area, then one of the important things to look at is the how to select these algorithms. If you have the reconfigurable architecture, but it is not useless, it will be useless if you don't know how to select which algorithm or which word length for a given scenario, or how to identify the environment, and based upon that you need to select or adapt your algorithm. Similarly, there are in the last 4-5 years there are change detection algorithms are being proposed for the quasi-stationary environment, and how to they are really memory intensive algorithm, because they depend upon the history of the say last some window based history, and which takes a lot of memory requirement. So a lot of work needs to be done in this algorithm, how to map them on the hardware. So, or to summarize, the hardware may not be hard anymore. Means some people now may not find it to implement any algorithms hard. Implementation is not that difficult, but it is different. So we need to there should be a strong co-design needs to be done between the hardware experts and the theory expert, so that to make sure that whenever we design the algorithms, they are feasible on the hardware. And the last slide, so as we have discussed, when we map the algorithms on the hardware, we need to take into account the hardware software co-design, the reconfigurable architecture, as well as intelligence to make the architecture reconfigurable. And the same concept is being applied to the other domain. For example, if you take into the deep learning algorithm, you have the multiple layers, and you need to decide which layers will put into the which part of the architecture, and how to add the reconfigurable. So very limited work has been done in this domain. And the same is true for the wireless physical layer, where you have the different baseband processing algorithm, and you need to switch between the hardware and software depending upon your area and latency requirement. And with the way the people are talking about the 6G, it may happen that the both of them will merge together, and we'll see that there will be a lot of intelligence being added at the file layer. Okay, so with this I'll end my talk. I'd like to thank COMSNET again for giving us the time for presenting the tutorial.
Thanks, Sumit. There is one question
Okay.
in the audience. There's a question from Rahul from TCS. Are FPGA and MSOC used only in base stations which work as edge devices, or even other?
Yeah. So very good question. So that's why the scalability comes into the part. So if you talk about the base station, in case of the base station, there are MP-SOCs are being used, but there are simpler version of MP-SOCs, which we can also talk it as a Zinc SoC. Even simpler version of the Zinc SoC, where you have single core processor and very simple FPGA, very small scale FPGA. So you can see that this architecture is scalable. That for the base station, you need a quad core processor and the larger FPGA, but the same version with the single core processor without the GPU and the smaller FPGA is available. So depending upon your application, you can depending upon whether you want to implement at the sensor level, or at the gateway level, or at the base station level, you need to choose the appropriate SoC. And if you want more about this one, there is a recent book on the Zinc MP SoC from the Xilinx and one of the university in collaboration with this, and they have explained in detail the applications of the different variety of the SoC architecture for the different case scenarios.
So thanks, Sumit. So I think there is no other question. Is that right?
Yeah, I don't see any other question.
Yeah. So then we would like to thank the speakers, and I would request Nadim to give his final remarks, and he has something to share on the screen. So Nadim, yeah,
Sumit,
please.
can you stop sharing the screen?
Yeah.
Thank you. So thank you very much, Sumit and Manjesh, for the excellent tutorial. I hope the audience enjoyed it, and it was very informative and very in-depth session on distributed learning algorithms for wireless networks. And it is my pleasure to give a recognition of contribution to both the speakers. So we have a virtual memento for Manjesh here. I'm displaying. I hope you are able to see it. So
Yes.
congratulations, Manjesh, and thank you very much for this tutorial session. And I invite the audience to have a round of applause for Manjesh. And following from Manjesh, again, thanks to Sumit for the very in-depth session in the second half. And here's a certificate for Sumit, and we'll be mailing the mementos to both the speakers. And once again, thanks to both the speakers for taking time out and speaking to our audience. And thanks to everyone who joined in. This was a very good session again, the third session as part of this tutorial series. And I welcome you all to join the last session at 5 p.m., where we'll be talking about 5G. And thanks everyone for attending. And with this, we end this third tutorial session of COMSNETs.
Yeah, thanks,
Thank you.
Arpan
Yeah.
and Nadeem again. Thanks a lot.
And thank you to Advait for hosting this session.
Yeah, thank you.
We can close now. Thanks. Thanks everyone. Goodbye.
Bye.
Thank you, sir. I'm closing the session.